Welcome to the comprehensive training program for the Microsoft PL-500 exam. In this introductory chapter, we will establish the fundamental context of robotic process automation within the Microsoft ecosystem. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Microsoft Corporation in any way. This content is for educational and exam preparation purposes only and does not guarantee a passing grade on the official certification exam. All trademarks belong to their respective owners. Robotic process automation is often misunderstood as simply recording clicks, but it is fundamentally about bridging the gaps between disparate legacy systems and modern cloud architecture. By leveraging Power Automate, you are not just automating a task, you are integrating manual desktop interfaces into a cohesive, manageable, and scalable business logic layer. This course transforms your existing development intuition into a disciplined approach for crafting robust RPA solutions. You will learn to navigate the intricate balance between attended automation, which aids human productivity, and unattended automation, which functions as an autonomous digital workforce. Our journey begins by examining the core architecture of the Power Automate ecosystem, specifically how desktop flows communicate with the cloud control plane. We will move beyond basic concepts to address the configuration of development environments, the necessity of Dataverse for structured storage, and, crucially, the governing principles that keep your automation enterprise-grade. Many developers fail the PL-500 because they focus solely on the script rather than the infrastructure. We will ensure your solutions are secure, compliant, and architected for long-term maintenance rather than temporary convenience. As we progress through the curriculum, you will master the nuances of UI automation, dynamic selector handling, and sophisticated exception management. We will explore how to treat error handling as a primary design concern rather than an afterthought, ensuring your bots remain resilient in the face of unpredictable interface changes. Furthermore, the course covers the integration of AI Builder and custom connectors, which allows your bots to interpret unstructured data and interact with services beyond the standard Microsoft stack. These modules are specifically curated to align with the objective domains defined by Microsoft for the PL-500 certification. I encourage you to adopt a critical mindset throughout this course, questioning how each component fits into the larger application lifecycle. Whether we are discussing machine groups, on-premises data gateways, or monitoring analytics, the goal is to think like a professional automation architect. You will gain the confidence to design, develop, and deploy solutions that meet rigorous business requirements while passing the certification requirements. Let us now begin this learning journey together. I look forward to our next session together. Welcome to the second chapter of our journey, where we will establish the fundamental principles of robotic process automation and explore how they align with business objectives. By the end of this module, you will have a clear understanding of the core concepts required to pass the PL-500 exam and architect robust automation solutions. Robotic process automation, or RPA, represents a shift in how we approach the digital plumbing of modern enterprises. At its core, the technology is designed to mimic human interaction with software to execute repetitive and rules-based tasks across various applications. If you have spent any time in an office environment, you are likely intimately familiar with the swivel chair integration, where a human manually logs into one system, copies data, and pastes it into another. RPA aims to replace these high-volume, low-value human interactions with software bots, thereby allowing employees to focus on cognitive tasks that actually move the needle. When we talk about transformation, we are not just discussing cost reduction. We're talking about increasing accuracy and consistency, as a bot will faithfully execute the exact same procedure every time without fatigue or emotional volatility. The industry use cases for RPA are broad, spanning finance, human resources, and supply chain management. Consider a scenario involving invoice processing, where an organization receives thousands of PDFs via email and must extract data to enter into an ERP system. A manual process here is prone to entry errors, slows down the accounts payable cycle, and consumes valuable time that could be spent on financial analysis. By automating this, the bot handles the document classification and data entry, leaving a human only to handle exceptions or anomalies identified by the business rules. This shift from manual execution to orchestration enables businesses to scale their operations without necessarily increasing their headcount in direct proportion to the volume of work. Effective RPA strategy involves identifying processes with stable, high-volume traffic and clear digital footprints rather than trying to automate chaotic, manual processes that lack a defined sequence of operations. When we differentiate between attended and unattended RPA, the distinction lies in the nature of interactivity and the hosting environment. Attended automation is closely tethered to a user workstation, functioning essentially as a digital assistant that acts upon immediate triggers or commands provided by the human operator. In this model, the bot and the human share the control of the desktop environment to complete complex transactions that require human judgment or security credentials. Conversely, unattended RPA executes autonomously, often running on dedicated virtual machines or background servers where no human presence is expected. These bots consume a queue of work and process it according to a defined schedule or event-driven architecture, making them indispensable for high-volume background tasks. Choosing between these two requires a careful assessment of your business processes, particularly regarding the need for human oversight versus the demand for batch-oriented horizontal scalability. Selecting the appropriate topology for your automation requires an objective assessment of multiple technical and operational constraints. Scalability is obviously a primary concern, as unattended bots on cloud-hosted virtual machines offer much higher throughput for enterprise-wide initiatives than relying on a small fleet of local user workstations. Security protocols also differ significantly because attended bots operate under the user's identity, while unattended bots often require service accounts with scoped permissions to ensure the principle of least privilege. You must also account for licensing costs and infrastructure overhead, as unattended automation implies the maintenance of virtual machine environments and potential additional licensing requirements from the Power Platform ecosystem. Developing a solid return on investment is not merely about calculating the hours saved. It is about examining the total cost of ownership, inclusive of maintenance, exception management, and the occasional need to refactor workflows when the underlying application interfaces undergo changes. See you in the next lecture. Welcome back. In this lesson, we explore the architectural backbone of Microsoft Power Platform, specifically as it pertains to robotic process automation. To understand RPA within the Microsoft ecosystem, you must first perceive the Power Automate architecture as a hybrid bridge between cloud orchestration and local execution. At the highest level, the Power Automate cloud service acts as the control plane where your logic resides, orchestrating triggers and managing the flow lifecycle through the Microsoft Dataverse. Dataverse serves as the canonical storage for your flow definitions, run history, and runtime status, ensuring that all state information is available globally. When an automation requires interaction with legacy desktop applications, it offloads these tasks to the Power Automate desktop client installed on a local machine or virtual machine. This transition is managed by the machine runtime, which facilitates the secure handshake between the cloud service and the local host. Understanding this distributed approach is crucial because the performance and reliability of your automations depend heavily on how these distributed components communicate and maintain state. The interaction between these components relies on specific networking and security configurations, most notably the on-premises data gateway or the direct cloud-to-machine connectivity provided by the machine runtime. When you design an automation, you are essentially defining a contract between the cloud flow, which handles API-based orchestration, and the desktop flow, which handles user interface interaction. The machine runtime environment acts as the bridge that listens for commands from the cloud and transmits execution logs and telemetry back to Dataverse. Security roles and administrative boundaries in the Power Platform allow you to isolate these automation assets, ensuring that only authorized users or service principals can trigger sensitive desktop flows. Moreover, data loss prevention policies provide an essential governance layer that restricts data movement between connectors, effectively preventing the accidental exposure of sensitive information during the execution of an automated task. When we map the end-to-end data flow, we start at a cloud-triggered event, such as an incoming email or a scheduled time, which initiates a cloud flow. This cloud flow then triggers a desktop flow execution by making a request to the machine runtime associated with specific target infrastructure or machine groups. The machine runtime verifies the request credentials, ensures the local agent is active, and then delegates the task to the desktop flow execution engine. Once the local task completes, the results and status codes are sent back to the cloud, allowing the cloud flow to continue its work based on the output of the local automation. This entire communication chain happens over encrypted channels, utilizing secure authentication tokens to verify the identity of both the cloud service and the local machine. It is a robust, asynchronous system designed to handle the complexities of local execution while maintaining the enterprise-grade management capabilities expected from a cloud-native platform like Power Automate. Effective RPA deployment requires attention to these architectural boundaries, particularly when considering how machine groups offer scalability and load balancing. By grouping multiple machines into a single machine group, you allow the Power Automate cloud service to handle queuing and distribution of tasks across the available physical or virtual resources. This prevents bottlenecks and ensures the resilience of your automation ecosystem against individual machine failures or maintenance schedules. From a compliance perspective, you must carefully segment your environments to ensure that development, testing, and production runs are physically and logically separated within the Dataverse. These environments function as silos that encapsulate your flows, connection references, and security settings, preventing unauthorized cross-contamination of your automated processes while maintaining a streamlined path for promotion between environments. Mastering these components is essential for anyone aiming to design reliable, scalable, and secure automations that reside within the enterprise scope. You now understand how the orchestration layer integrates with the local execution layer and how security policies maintain the integrity of your automation environment. This architectural grounding ensures that when you start building flows, you are doing so with a clear picture of how data moves from your cloud triggers to the applications running on your desktop. We have covered the structural interplay that defines the Microsoft RPA ecosystem, which will serve as the foundation for the more tactical tasks we will discuss next. Proceed to the next section when you are ready. Welcome back to our journey toward mastering the PL-500 certification, where today we focus on the fundamental architectural distinction between attended and unattended automation. By the end of this session, you will grasp the structural requirements necessary to architect robust solutions that reliably execute in either user-driven or background environments. When we approach the architecture of robotic process automation in Power Automate, the primary distinction between attended and unattended modes dictates every design decision we make. Attended automation is intrinsically tied to a live user session, acting as an intelligent assistant that runs on a local workstation to supplement human tasks. Because the human operator is physically present, these automations can rely on user-initiated triggers and dynamic, interactive input. Conversely, unattended automation is designed for autonomous execution without the presence of a human, essentially operating as a digital workforce serving a queue. This shift requires us to move away from local user context dependencies toward hardened, secure machine-based execution environments that prioritize scalability and resiliency. Configuring an unattended environment requires a departure from standard desktop practices because the automation must exist independently of a logged-in user session. We achieve this by deploying desktop flows through machine runtime groups, which manage the allocation of tasks across multiple virtual machines or physical servers. A central challenge here involves handling locked Windows sessions, as the bot requires a mechanism to simulate an interactive session without exposing sensitive desktop state information. To facilitate this, we configure the machine environment to handle screen resolution consistently, ensuring that UI elements remain locatable even when the physical monitor is absent. Furthermore, secure credential injection becomes non-negotiable, as the automation must retrieve credentials from a secure vault rather than relying on cached user tokens or manual entry. In contrast, attended automation design focuses on minimizing cognitive load for the human operator while providing seamless handoffs between the bot and the worker. We treat the human as a partner, meaning the user interface must be clean, providing real-time status notifications at every critical junction of the process. Effective attended solutions implement validation mechanisms that confirm data integrity before passing control to the automation, ensuring that the bot is not attempting to process corrupted input. When designing these flows, we often utilize input boxes or message dialogues to request missing parameters directly from the user, which reduces the need for constant background monitoring. Graceful handoffs are essential here. Once the automation completes its portion of the task, it should return control to the operator with clear instructions on the next logical steps. Managing concurrent execution poses the most significant hurdle for unattended scaling, requiring a robust queuing mechanism to handle high volumes of work. We utilize Power Automate queues to decouple the trigger from the execution, allowing multiple bot instances to contend for work items based on availability. This pattern ensures that if one machine fails due to a system error or network oscillation, the item can be safely returned to the queue and reprocessed by another node in the group. We also implement retry policies at the cloud flow level, which act as a safety net when a specific machine resource becomes temporarily unresponsive. This architectural layer provides the observability required to track the life cycle of a work item, from inception to completion, which is vital for compliance and auditing. Security remains the backbone of both paradigms, though the implementation details shift based on the required privilege level of the unattended agent. For unattended runs, the service account must possess the minimum necessary permissions to perform the task, and we avoid the use of shared administrative credentials at all costs. We categorize our execution permissions by ensuring the machine is part of a domain or tenant-managed structure that respects existing group policies while allowing for the necessary interaction with legacy and modern applications. Because the automation runs server-side, it is susceptible to drift if the host environment is not strictly governed, making configuration management a core component of the architectural lifecycle. By isolating the execution environment from the developer workstation, we protect the production process against inadvertent modifications and maintain a consistent baseline for our bot behavior. See you in the next lecture. Welcome back. In this chapter, we will focus on the essential task of preparing your local workstation for robust robotic process automation development, ensuring your environment is technically ready for the requirements of the PL-500 exam. Building a functional development environment for Power Automate Desktop requires more than simply running an installer. It demands a systematic approach to system prerequisites and local machine configuration. Before initiating the installation process, you must ensure that your host machine meets the hardware and operating system requirements mandated by Microsoft, typically involving a supported Windows 10 or 11 version with the proper .NET framework support. Once the base operating system is verified, you proceed to download and install the Power Automate desktop application from the Microsoft portal, which acts as the execution engine for your local desktop flows. The installation process itself will prompt you to provide necessary administrative permissions, as the software needs to interact with low-level Windows APIs to perform UI automation tasks across various desktop applications. During this phase, it is prudent to confirm that your user account has the required local system privileges, as restrictive group policies or missing permissions frequently prevent the creation and testing of screen scraping automations. After the core software is operational, your immediate focus should shift toward browser integration, which involves installing and enabling the official Power Automate browser extensions for Microsoft Edge, Google Chrome, and Mozilla Firefox. These extensions are not optional. They serve as a bridge between the Power Automate engine and the document object model of web pages, allowing for reliable interaction with web elements during data extraction tasks. Without these extensions properly configured and enabled in your browser settings, your flows will inevitably fail to recognize web elements, rendering your automation efforts ineffective and frustrating. Connectivity remains a critical aspect of your development lifecycle, specifically when you are attempting to link your local machine to a broader Power Platform environment in the cloud. You should navigate to the Power Automate Cloud portal to verify that your machine has successfully registered as a participant in your designated environment, as this registration is what allows the cloud orchestrator to trigger runs on your local infrastructure. If you find that the machine status shows as offline or disconnected in the portal, you must inspect the local machine runtime application to ensure the user identity associated with the service is authenticated correctly against your Microsoft Entra ID credentials. In scenarios where your development work takes place within managed corporate networks, you may encounter connectivity bottlenecks caused by restrictive firewall rules or required proxy authentication protocols. To resolve these, you must manually configure the machine proxy settings to permit traffic between your workstation and the Power Platform service endpoints. ensuring that Power Automate can communicate status updates and receive workflow instructions without interruption. Neglecting these network configurations often manifests as persistent gateway errors or timeout exceptions, which can be difficult to diagnose if you're not monitoring the logs generated by the local runtime service. Establishing a secure, verified handshake between your desktop machine and the cloud environment is therefore an absolute prerequisite for any professional RPA developer aiming to scale automations beyond a single machine. Beyond mere installation and connectivity, you must also cultivate an environment that fosters frictionless testing by configuring appropriate environment variables and local system settings. Environment variables allow you to externalize configuration data, such as file paths, API endpoints, or database connection strings, ensuring that your desktop flows remain portable across different staging and production environments. By defining these variables at the system level, you prevent hard-coding sensitive values into your flows, which is a significant security risk and a common failure point for maintainability in large-scale enterprise deployments. Furthermore, you should familiarize yourself with the machine management view in the cloud portal, which allows you to group machines and manage runtimes effectively, especially when preparing for unattended automation scenarios where no human user is present to supervise the execution. Understanding the interaction between local Windows service permissions and the Power Automate cloud service is paramount for ensuring that your automated scripts have the necessary authority to read, write, and execute tasks across the full breadth of the local file system. Whenever you encounter issues with the local runtime, start by reviewing the diagnostic logs that are generated locally, as these often contain the specific error codes related to authentication failures or resource access restrictions. By systematically verifying these components, the installer, the browser hooks for web automation, the network proxy configurations, and the machine-to-cloud registration, you effectively reduce the time spent troubleshooting and increase the time spent building reliable, scalable RPA solutions. See you in the next lecture. Welcome to our exploration of Dataverse, the robust data platform specifically engineered to support the complex requirements of enterprise-grade automation. In this chapter, you will master how to leverage Dataverse as a persistent, secure, and scalable foundation for your Power Automate RPA projects. If you are serious about passing the PL-500 exam and building professional-grade solutions, understanding Dataverse is non-negotiable. This course provides the architectural insights and practical configuration knowledge required to transition from basic script-based automation to resilient, scalable enterprise workflows. By the end of this journey, you will know exactly how to manage automation states and security, ensuring your bots are production-ready. In this series of lessons, we will dissect exactly how Microsoft Dataverse functions as the backbone for your RPA solutions. We will cover the practical application of standard and custom tables, the nuances of defining data relationships, and the utilization of choice columns for state management. Furthermore, we will delve into the technical mechanisms by which Power Automate Desktop maintains telemetry and audit logs directly within the Dataverse environment. You will also learn how to apply stringent security models, including table permissions and column-level security, to satisfy the principle of least privilege. We intend to demystify how these operational queues and configuration settings integrate with your existing cloud orchestrations. By aligning your automation design with these platform capabilities, you ensure that your data remains consistent and your audit trails stay indisputable across the entire lifecycle. Prepare yourself to move beyond simple variable handling. We have a solid plan ahead to ensure you are ready for the core exam objectives. I will see you in the next lecture. Welcome back to the course. In this chapter, we explore RPA governance and security, detailing the essential controls and frameworks required to scale automation maturely across your enterprise. Enterprise-scale robotic process automation requires more than just functional flows. It demands a rigorous governance framework to ensure data sovereignty and operational integrity. When deploying Power Automate, you must view the platform not as a collection of isolated scripts, but as a critical infrastructure component subject to corporate security policies. The primary mechanism for enforcing these boundaries is the Power Platform Admin Center, where administrators exert control over tenant-wide settings and environment strategies. Establishing clear separation between development, testing, and production environments is the first step toward mitigating risk. Furthermore, by implementing data loss prevention policies, you can explicitly restrict which connectors interact with one another, thereby preventing sensitive data from leaking into unauthorized third-party services. These policies allow you to categorize connectors into business, non-business, or blocked groups, effectively boxing in the data flows that your automation bots utilize. Governance also requires a sensible approach to citizen development, which is often the most significant point of friction in an enterprise IT strategy. Instead of relying on rigid, manual gatekeeping, you should implement guardrails that empower users while maintaining systemic control. This involves defining the specific scopes and permissions for developers, ensuring that service accounts possess only the minimum privileges required for their specific tasks. When an automation requires access to sensitive credentials, you must avoid the amateurish pattern of hard-coding passwords within a flow. Instead, leverage Azure Key Vault to centralize and secure secret management, ensuring that your flows programmatically retrieve keys at runtime. This practice significantly reduces the blast radius of a potential credential compromise and aligns with standard security compliance requirements. Beyond infrastructure and credentials, we must consider the data handled by the automation processes themselves. Any input or output containing personally identifiable information or regulated data needs to be treated as high risk by default. It is standard practice to obfuscate sensitive information in logs and during runtime execution, ensuring that diagnostic data does not inadvertently expose customer records or proprietary secrets. Before any workflow moves from a development sandbox to a production target, it must undergo a comprehensive security and architectural review. This review process functions as a checklist item in your lifecycle management, validating that exception handling does not leak data and that connectivity is limited to essential endpoints. Maintaining these standards ensures that your RPA deployment remains compliant with internal and external security audits. Look forward to discussing the practical application of these concepts in the next segment. Welcome to the chapter on developing desktop flows, where we will translate manual processes into structured, automated scripts. We begin this journey by mastering the Power Automate desktop environment and creating your first functional automation project. When you first launch the Power Automate desktop console, you are met with a dashboard that serves as the command center for your automation lifecycle. To create your first flow, you initiate a new project, which opens the designer interface, a robust IDE tailored for building RPA solutions. The interface is logically divided, with the Actions pane on the far left featuring a catalog of over 400 modular operations. In the center lies the canvas, the primary workspace where you drop and connect these actions to define the execution flow of your script. To the right, the variables library keeps track of the data states, providing transparency into what information is being passed between operations at any moment. Understanding these quadrants is fundamental because it allows you to maintain focus while building increasingly complex logical chains. Before you drag your first action, spend a moment in the global settings to define your console environment and default timeouts. These configurations ensure that your flows interact with the underlying operating system in a predictable, stable, and performant manner. The most efficient way to architect your initial automation is through the utilization of the built-in UI and web recorders. When you activate the recorder, the engine initiates a tracking session that watches your mouse movements, clicks, and keystrokes in real time. Whether you are interacting with a legacy Windows desktop application or a modern web browser, the recorder captures these interactions and translates them into discrete, high-level action blocks. Once you stop the recording, the designer populates your canvas with these generated steps, providing a baseline script that you can immediately inspect. This process is rarely a one-shot success story, as you must often refine the captured data to ensure the automation is not just functional, but maintainable. You should approach recorded actions as a scaffolding rather than a finished product, meaning you must inspect the generated selectors for resilience. If the recorder captures a fragile element reference that might change between sessions, replace it with a more robust, absolute, or relative selector. Reading the generated actions requires a shift in perspective, moving from a user-centric view to a component-based architectural view. You will observe that the designer serializes your recorded interactions into a top-to-bottom sequence of operations that can be reorganized by simple dragging. If you identify a logical grouping of actions that performs a single business task, you hold the power to reorganize these into clearer, more modular structures. A flat, unorganized list of actions becomes difficult to debug as the project expands, making early adherence to sound structural patterns vital. By grouping these initial actions into logical segments, you lay the groundwork for modularity, which is essential for error handling and long-term script maintenance. Furthermore, the ability to interpret these actions allows you to insert manual logic, such as wait commands or variable assignments, right where the recorded flow needs them most. This mix of recording for speed and manual refactoring for precision represents the hallmark of a professional RPA developer. Finally, you must run the flow in debug mode as your primary verification step to ensure that the orchestration behaves as expected. The designer provides a built-in playback engine that highlights the current action being executed, allowing you to watch the automation unfold while inspecting the variables pane. If an action fails, you can pause execution, modify the parameters, and resume without needing to start the entire process again. This tight feedback loop is what differentiates a novice approach from a professional methodology. Always observe the state of your variables after every iteration to confirm that the data captured from the UI matches the required format for your next processing step. With these foundations in place, you are ready to transition from simple recording to creating complex, dynamic workflows that can handle varied business scenarios with ease. See you in the next lecture. Welcome back. We are now entering the chapter on UI automation within Windows applications. We will explore how to interact with legacy and modern desktop software using the underlying frameworks that power your desktop flows. When we talk about UI automation and Power Automate, we are essentially discussing the ability of the software to programmatically interface with the operating system's graphical elements. At its core, the Windows platform relies on several accessibility frameworks that allow assistive technologies, and by extension, our automation bots, to read and interact with application controls. The primary frameworks you will encounter are UI automation, often abbreviated as UIA, and the older Microsoft Active Accessibility, known as MSAA. These frameworks provide a mechanism for the application to expose its structure, property values, and control states to the operating system. Power Automate Desktop sits on top of these APIs, translating your design time configuration into actual interactions that the Windows kernel understands. Understanding this dependency is vital because it explains why some applications are naturally easier to automate than others. If an application developer strictly follows the guidelines for these accessibility frameworks, the bot will communicate with the controls directly and reliably. If they do not, we often find ourselves needing to fall back to less deterministic methods like coordinate-based clicking or image recognition, which we should always avoid if a direct programmatic link is available. To start automating a Windows application, the first step is usually to launch the instance correctly using the appropriate action. Once the application is active, Power Automate must successfully attach to the specific window and identify the specific control, be it a text box, button, or checkbox, that requires interaction. This process relies on selectors, which are a collection of attributes that uniquely identify a UI element within the application's tree hierarchy. When dealing with standard Win32 applications, you might notice that some elements possess unique IDs, while others might rely on their name property or their relative position in the form. If you are faced with a complex grid or table, you will often use data scraping techniques to extract information into a collection variable for later processing. It is helpful to consider these controls as objects with specific properties that we can both read from and write to during the execution of our flow. For example, setting the text of a field is merely a matter of targeting the control and invoking the appropriate input action. The engine then handles the low-level Windows messages required to simulate the keyboard input or programmatic value assignment needed to update that UI element. There are inevitably scenarios where applications do not behave as perfectly as our design time environment would suggest. You may encounter interfaces that are rendered dynamically, or perhaps legacy software that does not properly register its elements with the underlying UIA provider. In these edge cases, managing control focus becomes a critical design consideration because actions might fail if the window loses focus, or if a modal dialog unexpectedly pops up, obscuring the primary interface. We can mitigate many of these issues by using simulated mouse clicks or direct keyboard shortcuts to navigate through the application. Sending keystrokes directly to an active window is often more robust than attempting to click on every single button, especially if the layout is prone to shifting. Furthermore, if you're working with non-standard windows that defy traditional element identification, you can leverage image-based automation as a last resort, though you must be aware that this reduces the portability and reliability of your automation solution. Always strive to maintain the highest level of abstraction possible, relying on control identifiers rather than visual coordinates or image matching whenever the underlying technology allows for it. Moving forward, you will need to apply these patterns consistently throughout your projects to ensure your automations are resilient to interface variations. As you build your desktop flows, always observe the hierarchy of the application interface and attempt to anchor your selectors to stable, static elements rather than those that are subject to change. By mastering these foundational UI automation techniques, you position yourself to handle a wide variety of Windows-based business applications, regardless of their age or complexity. Remember that each interaction with a UI control is an opportunity to introduce either stability through precise selector design or fragility through reliance on volatile properties. Focus on creating flows that interrogate the state of the interface before attempting an interaction, such as waiting for a button to become enabled before asserting a click. This proactive approach will save you countless hours of troubleshooting and debugging as your automation library grows and your project requirements become more sophisticated. I will see you in the next part of our journey. Welcome to this new chapter where we will master the intricacies of web automation and browser-based interactions. We will learn how to build resilient automation sequences that interface directly with complex web applications across modern browsers. When we talk about web automation in Power Automate Desktop, we have to look past the superficial layer of clicking buttons and typing text into input fields. The foundation of a stable web flow is the Microsoft Power Automate browser extension, which acts as the mandatory bridge between your flow logic and the browser's document object model. Without this extension, the automation engine is effectively blind to the granular details of the web page, leaving you to rely on brittle, coordinate-based mouse clicks. By ensuring the extension is installed and active, we gain the ability to inspect elements by their unique design attributes, such as ID, class, or XPath. This level of precision is the difference between a bot that runs reliably overnight and one that fails every time a designer moves a button on the web page. We must treat these browser extensions as a critical dependency in our architectural decision-making process. Interacting with web elements requires a shift in how we perceive time during the execution lifecycle. Web applications are notoriously asynchronous, often loading content dynamically via background scripts long after the initial page structure has been rendered in the browser. If we try to interact with an element before it is fully present in the DOM, our automation will throw an exception and terminate prematurely. To build reliable flows, we must move away from static delays, which are often unpredictable and detrimental to overall performance. Instead, we should implement explicit wait strategies that verify the presence, visibility, or state of specific web elements before triggering an action. By using actions that poll the browser for the existence of an object, we create a synchronous reaction to an asynchronous process, effectively hardening our scripts against slow network conditions or heavy server-side processing demands. Managing the browser lifecycle is just as significant as interacting with its interior contents. A robust automation routine should assume responsibility for its environment, starting with the proactive clearing of session data like cookies and caches if the scenario requires a fresh login state. We need to handle the nuances of modern web interfaces, including the occasional emergence of unexpected pop-up alerts or dynamically generated browser tabs. Power Automate Desktop provides specific actions to attach to existing sessions or launch new instances, allowing us to manage the browser lifecycle from initialization to termination. When downloading files automatically, we must ensure these actions are executed within a secure, predictable context to prevent file naming conflicts or unauthorized access to sensitive directories. These management tasks, while seemingly mundane, are the guardrails that prevent our unattended automations from entering an unstable, non-recoverable state during production execution. Form submissions and data entry represent the most common use cases for desktop flows, yet they are frequent points of failure if not handled with care. A standard form submission strategy should include a validation step after every primary interaction, ensuring that the target input field was indeed populated correctly before proceeding to the next action or clicking the submit button. When navigating through complex dashboards or nested portal structures, we should utilize logical navigation paths that account for potential redirection delays. By utilizing advanced CSS selectors or XPath expressions when the standard UI element detection fails, we provide a fallback mechanism that is far more durable than traditional recording methods. Always prioritize element attributes that are stable over time, as relying on paths that change with minor updates to the web application's DOM will inevitably lead to maintenance overhead that we would prefer to avoid while scaling our automation solutions. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of UI element identification and the architectural importance of maintaining a centralized repository for your desktop and web automation projects. When we interact with application interfaces, we are essentially communicating with an underlying hierarchy of nodes. Power Automate Desktop provides a UI element picker that acts as our primary instrument for identifying these nodes within the accessibility tree. When you initiate the spying process, you are capturing a snapshot of the element's properties, which the engine then uses to construct a selector. This selector is not merely a string of text. It is the definitive roadmap that tells the bot exactly where to click, type, or extract data throughout the execution of a flow. Relying on default names provided by the recorder is a common pitfall that often leads to brittle automations. Instead, you must treat these elements as first-class objects within your design, ensuring that each captured control is assigned a name that reflects its functional purpose rather than its internal technical ID. The UI Elements repository pane serves as the single source of truth for all controls utilized across your desktop flows. When you capture an element, it is added to this structured list, allowing you to reuse the same control in multiple actions without redundant scanning. If an application's layout changes, having a centralized repository means you only need to update the selector in one location to propagate the change throughout the entire project. To manage this effectively, I strongly recommend implementing a logical grouping strategy that mirrors the structural flow of the target application. You should organize elements by screen or specific functional dialog, which significantly reduces cognitive load when navigating complex automation projects with dozens or hundreds of controls. Beyond simple organization, the depth of the element tree varies significantly between Windows applications and web-based interfaces. Desktop applications often expose a rich tree based on UI automation (UIA) frameworks, while web applications rely on document object model (DOM) structures. Understanding the nuances of these trees is critical when you encounter dynamic components that do not have static identifiers. When you inspect these trees, look for attributes that possess stability over time, such as automation IDs or unique labels, rather than volatile attributes like coordinates or indexes. A robust selector should be resilient enough to handle minor updates to the UI without requiring developer intervention, which is the hallmark of a well-architected RPA solution. Naming conventions should be established at the very inception of a development project to facilitate better maintenance and team collaboration. A standard convention, such as prefixing controls with their type like btn for buttons or txt for input fields, followed by a descriptive name like submit or customer last name, turns the repository into a readable document in itself. This clarity becomes invaluable when you return to a flow after several months or when passing the project to a colleague who did not design the original logic. You should also audit your repository periodically, removing unused elements to keep the metadata slim and manageable. Minimizing redundancy is not just about cleanliness. It is a defensive programming practice that prevents confusion and ensures the consistency of every interaction with the target application layer. By adhering to these systematic approaches, you transform the mechanical act of spying into a disciplined practice of interface modeling. You are creating a sustainable interface contract between your automation logic and the external software, shielding your business processes from unnecessary breakage. As you continue to build your expertise, Bear in mind that the quality of your element management will ultimately dictate the scalability and reliability of your entire RPA portfolio in a production environment. Focus on building clear, intuitive, and centralized structures that permit you to manage complexity rather than being overwhelmed by it. I will see you in the next lesson. Welcome back. In this lecture, we will explore the techniques required to master and optimize selectors for dynamic user interfaces within Power Automate Desktop. When building automation, the most common point of failure is an unstable selector. If you rely on generated selectors that contain hard-coded IDs or internal memory addresses, your flow will inevitably fail the moment the application undergoes even a minor update. A selector is, at its core, an XML representation of a UI element's path in the document object model, or the visual tree. If a specific attribute, such as an ID, is generated dynamically by the application runtime, which is common in complex web frameworks like React or Angular, the default selector created by the recorder will soon point to a non-existent location. We must move beyond the recorded default state to create robust, self-healing automation logic. The first step in hardening your selectors is to evaluate the attributes available in the selector editor. Often, a recorder will capture a long path involving multiple container levels that do not contribute to the uniqueness of the element. By analyzing the attributes, you can often identify static properties, such as a name, an inner text property, or a predictable tag structure. If an attribute changes, such as a timestamped ID or a transient session string, you should remove it from the selector tree entirely. Instead of relying on volatile data, prioritize attributes that remain consistent throughout the application lifecycle, even if they seem less specific at first glance. When absolute stability is not possible through attribute selection alone, we turn to the wildcard operator, commonly denoted by the asterisk symbol. This character acts as a placeholder for any sequence of characters, making it incredibly effective for attributes that contain varying data, such as dynamic session identifiers or file paths. If a window title changes based on whether a document is in read-only mode, using a wildcard allows the engine to ignore the prefix or suffix shift and lock onto the constant part of the title. However, exercise caution. If you make your wildcard usage too broad, you risk creating an ambiguous selector that could inadvertently match multiple elements on the screen, leading to unpredictable behavior during execution. For scenarios requiring more granular control than simple wildcards, regular expressions provide the necessary precision for matching attribute values. Power Automate Desktop allows you to enable regex support within the selector editing window, which transforms how the engine evaluates strings. By defining a pattern, you can successfully match elements that follow a specific format, such as an order number that always begins with a prefix, followed by a numerical sequence. This approach is instrumental when dealing with modern web applications where control paths change structure based on screen resolution or user permissions. By shifting from static string matching to pattern-based matching, you ensure that the automation logic remains decoupled from the transient nature of the user interface. The structural integrity of your selector is just as important as the individual attribute values being captured. In many complex applications, the DOM or visual tree depth might shift if a new container or menu wrapper is introduced during an update. Rather than relying on a brittle, deep path that traces every parent element to the root, we can utilize a partial selector approach. By focusing on the direct parent or the element itself, you reduce the surface area for errors when containers are reorganized or refactored by developers. This structural simplification is the difference between a flow that breaks every week and one that continues to run smoothly after major system upgrades. Optimizing selectors also requires understanding when to use relative indexing, especially in tabular data or repeating lists. When you are scraping or interacting with a row that exists in a dynamic grid, the row ID often changes based on the data displayed, but the position relative to other elements remains constant. You can combine index-based selectors with attribute overrides to ensure that you are always targeting the correct data point. By nesting these selectors correctly and ensuring that priority is given to the most stable attributes, you architect a solution that survives the transition between different environments. The goal is to move entirely towards selector definitions that reflect the permanent nature of the task rather than the ephemeral nature of the interface. Effectively managing these selectors is the hallmark of a senior automation developer. You should always treat the selector XML as a piece of code base that requires maintenance and refactoring, just as you would with your business logic. When you define these parameters, document the reasoning behind your choice of attributes to assist team members during future troubleshooting tasks. If a selector is failing despite your best efforts, use the selector highlight tool to verify that the element is consistently found across different states of the application. By continuously refining these paths and applying these strategies, you build resilience that scales across the entire enterprise. See you in the next lecture. Welcome back to our journey through the PL-500 curriculum, where we now focus on the critical task of data extraction and screen scraping. In this chapter, we will master the technical nuances of pulling information from legacy desktop software and complex web interfaces to turn unstructured UI elements into actionable data. Data extraction represents the bridge between static visual interfaces and the dynamic data structures required for automated logic. When you operate within Power Automate Desktop, you are rarely just clicking buttons, as the primary value lies in the data residing underneath those UI elements. To extract a single value, such as a customer ID or a total order sum, you must first identify the element through its selector and then retrieve a specific attribute property, typically the text or value field. While this works seamlessly for monolithic objects, extracting tabular data often requires a more holistic approach that parses the container structure of a grid or a list. By using the extract data from web page action, you can define a pattern once and let the engine traverse the entire table, mapping rows and columns directly into a data table variable. This transition from a visual representation to a programmatic object is what allows you to treat a web page as a data source rather than just a document. Scaling these extraction tasks to handle multi-page web grids introduces the challenge of continuous iteration. Web applications often implement pagination, which necessitates a flow that recognizes the next button and repeats the extraction action until all records are collected. You should design your loop structure to evaluate the existence of a navigation control after each batch extraction, ensuring the logic is robust against variations in result sets. This is a common requirement in data processing pipelines where you are expected to aggregate thousands of records across hundreds of pages. If you rely on hard-coded loops, your automation will inevitably fail when the search results decrease or increase unexpectedly. Instead, employ a condition that checks for the enabled state of the next page button, effectively creating a self-terminating loop that consumes all available data. In legacy environments, or when dealing with remote desktop protocols, standard UI selectors often become unavailable or unreliable. This is where optical character recognition enters the picture as a fallback mechanism for otherwise opaque content. Power Automate Desktop allows you to leverage engines like Windows OCR or Tesseract to interpret visual pixel data as readable text. This process is computationally more expensive than traditional selector-based extraction, so you should reserve it for scenarios where no DOM access or accessibility API is available. You essentially capture a region of the screen, transform that subimage into a character stream, and then perform text processing to locate the necessary data points. Although this method is prone to environment lighting or font rendering differences, it remains an indispensable tool for automating older enterprise software that predates modern web standards. When preparing to scrape data from virtualized environments or secured RDP sessions, the context of your bot's vision becomes the primary constraint. Since remote sessions often abstract the underlying UI elements into a single graphical stream, your local automation tools cannot see the internal structure of the remote application. Consequently, you must adopt a coordinate-based approach combined with OCR to identify elements relative to visual anchors. This requires a defensive programming style where you validate the presence of a known image or landmark before attempting to scrape. If your automation relies on RDP, your flow should include wait actions to account for latency, as the screen buffer might not refresh at the same pace as your local loop. Robust automation in these environments depends heavily on your ability to handle failure gracefully when the OCR engine encounters static noise or blurry text elements. Properly managing the variables generated by these extraction actions is equally important as the retrieval process itself. When you extract a table, Power Automate Desktop stores it as a specialized type that allows for further filtering, sorting, or writing to Excel. You should always aim to sanitize or trim the data immediately upon extraction to ensure that leading or trailing whitespace does not pollute your downstream operations. Many developers overlook the importance of explicit variable naming during this phase, which leads to maintenance nightmares when scaling the flow. By consistently naming your data tables and text variables, you ensure that anyone auditing your code can follow the transformation logic from the scrape action all the way to the final export. Effectively structuring your data tables at the point of ingestion is a hallmark of a professional RPA developer. See you in the next lecture. Welcome back. In this lecture, we will explore the mechanisms for managing variables and data types to ensure your automation logic remains robust and predictable. At the heart of any reliable automated process lies the effective management of state. When we design flows in Power Automate Desktop, we are essentially building a sequence of transformations that operate on data. Understanding how to store, initialize, and manipulate this data is not merely a technical requirement. It is a fundamental aspect of writing maintainable software. You will encounter various data types, ranging from simple primitives like integers, floating point numbers, and booleans, to more complex structures such as lists, data tables, and custom objects. Each of these types dictates how the automation engine handles memory and how you, as a developer, should interact with that data during the execution cycle. Scope is a concept that often causes confusion when transitioning from imperative coding to low-code environments, but it remains strictly deterministic here. A variable must be initialized within the scope where it is required, and understanding the boundary of these variables is crucial for preventing side effects that are difficult to debug. When you define a variable, you are establishing a contract for how that data persists throughout the flow. Initialization is the point where we assign an initial state to a variable, often using the set variable action or by capturing outputs from preceding actions. If you attempt to access an undefined variable, the runtime will throw an exception, halting the process, which is why explicit initialization is a core best practice. Data type conversion is a reality of working with disparate systems, such as reading text from a web page and needing to perform numeric calculations or date manipulation. Power Automate Desktop typically handles implicit conversion where possible, but relying on this behavior can lead to fragile automations. I prefer the use of explicit conversion actions, such as convert text to number or convert date to text, because they make the developer's intent clear to anyone reading the code. When you explicitly demand a specific type, you allow the engine to validate the input before it reaches a point of failure. This creates a fail-fast mechanism that is much easier to diagnose than an opaque runtime type mismatch error surfacing deep within a complex flow. Moving data between the Cloudflow environment and the desktop runtime is achieved through the configuration of input and output variables. This bridge allows your cloud-based orchestration to pass parameters into a desktop flow and receive results back upon completion. When setting these up, you must define the data type clearly so that the JSON serialization at the API boundary remains consistent. Failure to align your cloud-side data structures with the desktop-side flow parameters will result in serialization errors. Treat these inputs as external dependencies and always validate their content before passing them into the core logic of your automation to ensure your process is defensively designed. When dealing with sensitive information, such as passwords, API keys, or personally identifiable data, you must utilize the Mark as Sensitive property. In a production environment, logs and the variable viewer utility might inadvertently expose these values if you are not careful. By marking a variable as sensitive, you instruct the engine to obscure its value in logs and standard debugging outputs. This is a non-negotiable security requirement in enterprise environments where audit trails are reviewed by security teams. If you find yourself passing credentials through your flow, ensure that the very first action retrieves them from a secure vault and immediately mandates the sensitive attribute. Finally, the variable viewer utility is your primary window into the runtime state of your flow. During development and troubleshooting, pausing the execution at specific breakpoints allows you to inspect the current contents of your variables. This tool reveals whether a list contains the expected number of items or if a data table has successfully parsed the columns from an Excel file. Use this capability to verify the state of your application frequently. If you are struggling to understand why a branch of logic is not executing as expected, the answer is almost certainly sitting in the variable viewer, waiting for you to notice a subtle deviation in the data type or value. See you in the next lecture. Hello again. Let us discuss how to effectively manipulate textual data when it arrives in its raw, unstructured form. This chapter focuses on the necessity of transforming messy inputs into clean, ready-to-consume data structures for your downstream systems. In an ideal world, every data source would provide perfectly formatted JSON or cleanly separated CSV files that map directly to our internal data models. However, in the reality of RPA development, we are often forced to deal with screen output or legacy text files that contain extraneous whitespace, inconsistent character casing, or mixed metadata. Power Automate Desktop provides a robust suite of built-in actions designed to address these discrepancies without requiring custom script execution. When you encounter a block of text, the first step is often to standardize it using simple operations like trimming whitespace, changing the casing to match your target system's requirements, or using replace actions to remove prohibited characters. By chaining these operations together, you create a pipeline that gradually refines raw data into a usable variable. These actions are computationally inexpensive and should always be your first choice before reaching for more complex logic. Keeping your flows clean starts with knowing exactly which native transformation action fits the current requirement. When basic string manipulation falls short, regular expressions, or regex, become our primary tool for parsing complex textual patterns. Regex is not merely a feature of Power Automate. It is a universal language for pattern matching that allows you to identify, extract, or validate specific sequences of characters based on their structure rather than their literal content. Imagine you need to extract an order number from a multi-line invoice where the number's position varies, but its format, perhaps 3 letters followed by 7 digits, remains constant. You would utilize the parse text action configured with a regular expression to define this pattern precisely. This capability is essential for validating inputs like email addresses or isolating specific tracking numbers from unstructured logs. Mastery of regex allows you to treat text as a structured database rather than a static wall of characters. It requires a disciplined approach to pattern design, as well-crafted expressions prevent the common pitfall of capturing too little or too much information. Parsing flat files often involves isolating specific fields that are separated by delimiters like commas, tabs, or custom character sequences. Before we attempt to load such data into a data table or a list for later iteration, we must ensure that our splitting logic can handle the nuances of the input. For instance, a text block might represent a row of customer information where each field is delimited by a pipe character. Using the split text action, we can convert this single string into a list of items, where each index in the list corresponds to a known field in our destination application. It is vital to consider how your logic handles unexpected variations, such as an empty field or a column that occasionally contains the delimiter itself within the data. By combining these parsing techniques with standard string manipulation, you create resilient flows capable of translating disparate data sources into a consistent format that your target systems will accept without validation errors. The goal of these text operations is always to prepare data for successful entry into a target application or database system. If you fail to prepare your strings correctly, you will likely encounter downstream performance degradation or, worse, inconsistent data entry that ruins the integrity of your process. As you design these transformation sequences, verify the output of each action during the development phase to ensure that your intermediate variables maintain the expected structure. Do not assume the text will always arrive as expected, as human-generated reports and legacy system outputs are notoriously inconsistent. By strictly enforcing text formatting rules as a distinct stage within your flow's architecture, you isolate these logic concerns, making your desktop flows easier to maintain and troubleshoot. With a firm grasp of both native string actions and the power of regular expressions, you will find that even the most disorganized source text can be tamed into a reliable data flow. I will see you in the next lecture. Welcome back. In this lecture, we will explore the mechanisms for managing complex data collections, specifically focusing on lists and data tables within Power Automate Desktop. When we design automation workflows, we rarely operate on simple atomic variables like single strings or numbers. Instead, we frequently deal with structured data that represents multiple records or items, requiring us to manage these using list and data table variables. A list in Power Automate is a dynamic collection where we can store an ordered sequence of items, while a data table provides a more structured, grid-like format similar to an Excel sheet containing rows and columns. Understanding when to choose one over the other is a fundamental skill for any developer, as it directly impacts the efficiency and maintainability of your automation scripts. We typically start by initializing these collections using actions like create new list or create new data table, which serve as the foundation for our subsequent data processing logic. Once a container is established, we use actions such as add item to list or add row to data table to populate them with data extracted from UI elements, spreadsheets, or API responses. Manipulating these structures involves operations like removing specific entries, updating cell values based on coordinate references, or merging two separate collections into one unified resource. As your processes grow in complexity, you will find that these actions become the primary tools for state management throughout the lifecycle of your robotic process. Managing data tables requires a methodical approach, particularly when you need to interact with specific cells. You can address cells either by their numerical index or by referencing the specific column header, which is generally preferable for clarity and robustness against schema changes. When we modify a table, we often apply filters or sorting logic to organize the data before we perform bulk operations or output the final results. It is equally important to know how to clear data from these structures, especially when reusing variables across different iterations of a loop to avoid data contamination from previous runs. By mastering the sequence of adding rows, updating values, and sorting columns, you ensure that the downstream tasks receive clean and predictable datasets. This level of control allows you to transform raw, unstructured data into a business-ready format suitable for sophisticated reporting or further processing by other integrated systems. In modern integration scenarios, we often bridge the gap between human-readable interfaces and machine-readable data interchanges using serialization. We frequently receive structured data as JSON strings from REST APIs or other external services, requiring us to convert these raw strings into usable desktop flow objects. Power Automate provides direct actions to parse such JSON content into custom objects or directly map them into data tables for immediate integration into our automation flows. Conversely, when we need to push data back to a web service or store it for persistence, we must serialize our internal data tables or lists into a valid JSON or XML format. This process ensures that the data structure remains intact during transmission across the network or through a cloud-based API gateway. Being comfortable with this serialization pipeline is essential because it decouples our internal processing logic from the external data formats we consume and produce. I will see you in the next session. Welcome back. In this lecture, we will explore the nuances of advanced loop structures to control the execution flow of your robotic processes effectively. When building enterprise-grade automations, we rarely deal with linear, straightforward paths. Most business requirements involve repetitive tasks that demand precise control over how and when code blocks execute. In Power Automate Desktop, the loop action is our fundamental tool for index-based iterations. You define a start, a stop, and an increment value, allowing the engine to process a set number of cycles regardless of the data surface. This is particularly useful when you need to perform a task a fixed number of times, such as clicking a next button 5 times to navigate through a legacy pagination system. However, hard-coding these ranges can lead to brittle flows, so always prefer dynamic variables driven by your environment over static integers. Moving beyond simple indices, the for each loop acts as the workhorse for collection-based operations. When you retrieve data, perhaps by parsing an Excel sheet or gathering a list of files from a directory, the system returns a data table or a list variable. Placing these into a for each loop allows you to process every single row or file item sequentially without needing to manage the index manually. The power of this approach lies in its inherent safety. It handles empty collections gracefully by simply not executing the loop body. Always ensure that your input collection is properly initialized before you enter the loop, as iterating over a null or uninitialized object will trigger an error that breaks the flow execution. Sometimes, the logic dictates an indeterminate number of iterations, leading us toward the loop condition block. This mechanism functions similar to a while or do-while construct found in traditional programming. It evaluates a logical condition before each iteration, continuing the cycle as long as the evaluation remains true. This becomes indispensable when checking for the appearance of UI elements or waiting for a specific file to be created in a folder. Because this can easily result in an infinite loop, you must always incorporate a timeout mechanism or a safety counter variable to break execution if the condition remains unsatisfied beyond a reasonable threshold. Failing to implement these safeguards is a common source of resource exhaustion in unattended production environments. Managing these loops requires more than just knowing how to trigger them. You must understand how to influence their life cycle using flow control actions. The exit loop action provides a clean way to terminate a repetition immediately once your target is met, such as finding a specific invoice number in a large list. Conversely, the next loop action directs the execution engine to skip the remainder of the current iteration and jump straight to the beginning of the next cycle. Knowing when to use these is essential for writing clean, readable, and efficient automation designs. Overusing these controls can obscure your logic, so try to keep the business rules clear and the nesting as shallow as possible to maintain readability for others on your team. Nesting loops, while powerful, represents a common performance bottleneck in RPA development. When you place a for each loop inside another, the complexity increases exponentially for every nested level added. If you must process a large enterprise dataset, try to offload data filtering or aggregation tasks to the data source level whenever possible. Instead of iterating through 10,000 rows to find matches in a nested loop, perform a query that filters the data before it enters the desktop flow. Reducing the number of iterations directly contributes to the stability and execution speed of your unattended bots. Always profile the time taken by your loop operations to identify where optimizations can provide the most impact. See you in the next lecture. Welcome back, as we turn our attention toward the practical application of conditional logic within your Power Automate desktop flows to enable intelligent decision-making. When we design automation flows, we are essentially encoding human intent into a series of deterministic steps. However, real-world business processes are rarely linear. They encounter variations, exceptions, and branching paths that demand more than a simple sequence of commands. By implementing conditional logic, you allow the robot to evaluate current state information, such as the existence of a file, the text content within a browser element, or the value of a specific variable, to decide which path to take. Think of these conditions as the nervous system of your automation, where the flow senses its environment and reacts appropriately to ensure the process remains robust under changing input parameters. The most fundamental building block in this domain is the if action. It serves as a guardrail for your logic. You configure it to compare two values, verify a Boolean state, or check if a UI element is visible on the screen. Whenever you find yourself needing to evaluate multiple conditions simultaneously, you should avoid the temptation to create shallow, single-action checks. Instead, you utilize the combination of else and else if blocks. By nesting these logically, or more preferably, chaining them, you create a structured decision tree. This approach makes your code readable, maintainable, and, importantly, less prone to the logic bugs that often creep into poorly organized automation scripts. Consider a scenario where you are processing invoices. You might need to check if an invoice is over a certain monetary threshold, then check if it originated from a specific vendor, and finally confirm it has been digitally signed. Rather than creating deeply nested levels of if statements that look like a pyramid, you should aim for a flat, linear structure. An else if block allows you to test a new condition only if the previous one failed. This hierarchy keeps your logic clean and ensures that the flow control remains predictable for anyone tasked with maintaining the code later. Always remember that readability is the highest form of technical debt management. When you identify a single variable that can lead to many potential outcomes, the switch block becomes your most powerful tool for simplifying flow design. While you could technically implement a long chain of else-if statements, it often leads to cognitive overload for the developer reading the code. A switch block takes a single input, the variable, and maps it to various case labels. Each case acts as an isolated branch, clearly defining what happens for specific, discrete values. If the input doesn't match any of your defined cases, the default case ensures that the process doesn't simply disappear or hang, providing a safe landing zone for edge cases or unexpected data inputs. Effective automation design demands that you account for every potential state the system might enter. It is not enough to verify the happy path where data is perfect and files always exist. You must configure your conditional blocks to handle the absence of expected UI elements or the presence of malformed text inputs. Do not assume environmental stability. Assume that every input has the potential to trigger an exception. By explicitly defining conditional branches for both success and failure, you create resilient systems. A well-constructed logical structure is one where every possible branch is accounted for, leaving no path undefined or ambiguous. Mastering these conditional patterns will significantly elevate the quality of your desktop flows. You will find that your automations become both more flexible and easier to debug, as the logic is no longer hidden behind layers of complexity. As you continue your work with Power Automate, keep these structural principles in mind to maintain a high standard of professional development. I look forward to seeing you in the next lecture. Welcome back. In this lecture, we will explore the mechanisms for interacting with Excel and the local file system through Power Automate Desktop. When we automate administrative tasks, we often encounter the temptation to treat Excel as if it were a human user. This leads to the implementation of UI automation, where the robot captures mouse clicks, keystrokes, and window focuses to manipulate spreadsheets. While this approach is intuitive, it is inherently fragile and slow because it relies on the visual rendering of the application. Power Automate Desktop provides a dedicated Excel automation suite that interfaces directly with the Excel COM object model. By utilizing these native actions, we move away from visual emulation and into a direct programmatic conversation with the application instance. This shift not only increases the execution speed of our flows, but also significantly improves their reliability by removing dependencies on window states or screen resolution. To begin working with Excel, we typically launch a new instance or attach to an existing one if the file is already open. Once the application instance is established, we can perform operations such as reading and writing data to specific cells or ranges. It is important to emphasize that direct cell manipulation is far more efficient than copying and pasting data via the clipboard or UI interactions. When we read data, we store it in a data table variable, which provides an efficient structure for further processing within our flow logic. We can add worksheets, rename them, delete rows, or even execute existing macros within the workbook. When we conclude our data operations, we must remember to save the state or close the application instance, ensuring that we do not leave orphan processes running in the background. Moving beyond the boundaries of specific applications, we frequently need to interact with the broader file system. Power Automate Desktop offers an extensive library of actions to manage file operations, including creating, moving, renaming, copying, and deleting files and folders. These operations are essential for tasks like archiving processed reports, preparing input datasets, or cleaning up temporary directory structures. Unlike UI interactions, these operations interact directly with the operating system file provider, making them instantaneous and deterministic. We should always use the specific actions provided in the file and folder groups, rather than trying to build our own solutions using command line scripts. This standard architecture ensures that our flows remain maintainable and compatible with the monitoring tools built into the Power Automate ecosystem. Beyond file management, we are often required to handle configuration files or data exchange formats like CSV and XML. Reading these text-based files is a common pattern for parameterizing our automation workflows, as it allows us to store environment-specific settings outside of the hard-coded logic of the flow. When we read a text file, we typically assign its content to a variable that we then parse using text manipulation actions or convert into structured objects. CSV files are particularly powerful because they can be read directly into data tables, allowing us to leverage the same logic used for Excel workbooks. XML files require more nuanced handling, often necessitating the use of specialized parsing actions or custom expressions to extract nested values. Building our flows to support these file types increases the modularity of our automation projects significantly. Critical aspect of high-performance automation is the optimization of data processing through the use of background instances. When we do not need to observe the robot's interactions with an Excel file, we can configure our actions to execute in the background. This prevents the Excel window from stealing focus from other applications and avoids issues caused by accidental user interference. By prioritizing these direct, non-visual methods over UI-heavy techniques, we design robust bots that can handle high-volume data processing tasks without exhausting machine resources. This approach also allows us to manage multiple files concurrently if the architecture of the automation requires it. Adopting these headless execution patterns is a hallmark of professional-grade RPA development, shifting our focus from mimicking human behavior to purely logical data handling. As we continue to refine our automation strategy, we must ensure these file and data actions are properly wrapped within error handling blocks to catch common issues. File systems are dynamic and prone to access violations, locked files, or missing paths, so defensive programming is necessary. By explicitly checking for the existence of files or folders before attempting an operation, we can prevent a large number of avoidable runtime exceptions. This discipline, combined with the efficient use of the Excel automation layer, forms the foundation of reliable desktop automation. We are now prepared to approach complex data scenarios with a clear understanding of the tools available within our design environment. I look forward to discussing the next topic with you in the upcoming session. Welcome back to our journey toward mastering the PL-500 certification, where we will now build a robust foundation for exception handling within desktop flows. This chapter focuses entirely on the architecture of resilience, ensuring your automations survive the unpredictable nature of real-world enterprise applications. In the world of software development, we often strive for the happy path, but the true mark of a professional developer is how they handle the inevitable deviation from that path. Runtime errors in Power Automate Desktop are not merely inconveniences. They are signals indicating that the state of the machine or the target application no longer matches the assumptions baked into your automation logic. A system exception typically arises from environmental factors beyond your immediate control, such as a localized network drop, a failed file access permission, or an application that simply becomes unresponsive after a heavy data load. In contrast, business rule violations represent a logical failure where the automation reaches a valid state but fails to meet the specific criteria required for a successful transaction. Recognizing this distinction is critical because your strategy for recovery should differ significantly based on whether the fault lies in the infrastructure or the business logic itself. Consider the common triggers that lead to these failures, starting with selector failures, which occur when the underlying structure of a web page or a Windows application changes dynamically. When a UI element that was previously visible is no longer present, the engine cannot interact with it, triggering a terminal exception if not explicitly handled. Timeout thresholds represent another frequent point of failure, often resulting from slow system responses where an application takes just a second longer to load than the time allotted in your flow configuration. Meanwhile, file system exceptions are pervasive when processes attempt to write to locked files or navigate to paths that have been restricted by administrative security policies. Application unresponsiveness often compounds these issues, creating a cascade where a flow waits indefinitely for a window that has effectively hung due to a memory leak or a background process. If left unmanaged, these individual errors do not just stop an execution. They can cause significant data corruption or leave the machine in a state that prevents subsequent unattended tasks from succeeding. By default, without explicit error handling, Power Automate Desktop treats almost any exception as a fatal event that immediately terminates the execution flow. This default behavior halts the thread, sets the run status to a failed state, and reports back to the Cloudflow orchestrator, which then necessitates human intervention or a cumbersome retry process. This lack of resilience has downstream effects, particularly in transactional workflows where partially completed steps might leave external databases or legacy systems in an inconsistent state. When an unattended bot fails in the middle of a process and does not gracefully clean up its environment, subsequent runs may fail simply because the machine is dirty from the previous unsuccessful attempt. Consequently, understanding these foundations is not just about keeping the run history clean. It is about ensuring the integrity of the business ecosystem by allowing your flows to recover intelligently, or at the very least, terminate in a controlled, predictable manner. See you in the next lecture. Welcome back. Today, we are shifting our focus to the granular mechanics of exception handling at the level of individual Power Automate desktop actions. When we automate complex business processes, the assumption that every action will succeed on the first attempt is often the primary reason automations fail in production. Real-world systems are inherently unpredictable, particularly when interacting with legacy applications, network-bound web resources, or volatile user interfaces. Rather than allowing a single failed interaction to terminate an entire workflow, we implement localized error handling directly within the properties of individual actions. By opening the configuration pane of any automation step, you gain access to the on-error settings, which act as the first line of defense against transient instabilities. This is where we shift from reactive debugging to proactive resilience, ensuring that our bots handle environmental fluctuations with systematic intelligence rather than crashing unexpectedly. One of the most effective strategies for dealing with flaky actions, such as a page taking 5 seconds longer to load than anticipated, is the implementation of a retry policy. Instead of immediately surfacing an error, we instruct the engine to repeat the action a specified number of times before finally conceding failure. You can define the maximum number of retries and the exact interval in seconds between these attempts, which helps mitigate issues caused by temporary resource contention. A well-placed 3-second delay between 3 sequential retries often resolves issues that would otherwise trigger a fatal exception. By choosing these values thoughtfully, you strike a balance between allowing enough time for recovery and avoiding unnecessarily long execution times that hinder the overall throughput of your automation. Beyond simple retries, Power Automate allows for rule-based branching that determines the behavior of the flow when a specific exception occurs. If an action persists in failing after all retries are exhausted, you have the option to continue the flow execution, ignore the error, or choose a custom path. Choosing to run a specific subflow upon failure is a particularly powerful pattern, as it allows you to centralize recovery logic or perform cleanup tasks, such as closing a corrupted browser instance before restarting the process. Alternatively, you might trigger a notification or write to an internal audit log by invoking subflows designed specifically for incident escalation. This branching capability effectively compartmentalizes the failure, allowing the main logic to remain focused on the happy path while specific error handling subflows manage the anomalies. To make these decisions effectively, you must utilize the specific error codes and localized error messages that the platform provides during an exception event. When a failure occurs, the engine populates internal variables containing detailed diagnostic information that you can inspect to pinpoint the underlying cause. Instead of treating every failure as a generic obstacle, you can create logic that evaluates the error code to decide whether a retry is appropriate or if immediate termination is required. For instance, an error indicating a missing UI element might necessitate a different recovery strategy compared to a timeout error generated by a server-side API call. By dynamically reading these messages and status codes into your variables, you turn what would otherwise be a silent failure into a structured data point that informs the ongoing execution of your automation. When you treat each step of your workflow as a potential failure point, you naturally write more mature, production-ready code that respects the limitations of the environment. Integrating these settings appropriately transforms your desktop flows from rigid scripts into adaptable agents that can navigate the uncertainties of enterprise automation landscapes. I encourage you to revisit your existing action configurations to verify that you are leveraging these granular controls wherever network or application volatility is present. Consistency in how you apply these settings will lead to much more predictable outcomes for your stakeholders and fewer manual interventions for your support teams. See you in the next lecture. Hello, and welcome back. Today, we will explore the architecture of block-level exception handling to build resilient desktop automation flows. When we construct robust automation, individual action-level retries are often insufficient for complex business processes. A sequence of interdependent actions, such as logging into a legacy application, navigating to a specific module, and exporting a data report acts as a single logical transaction. If any part of this sequence fails, the entire transaction is compromised, and treating the failure as an isolated event often leaves the system in an inconsistent state. By wrapping these related actions within a try block, we gain the ability to manage the failure holistically. This strategic grouping allows us to define a centralized exception block where we can perform comprehensive cleanup and recovery operations regardless of which specific step within the sequence triggered the error. The primary advantage of block-level exception handling is the ability to maintain a clean application state after a fault. Simply ignoring an error and continuing execution often leads to subsequent failures caused by the residual effects of the aborted task. Within the exception block, we should implement logic that addresses the root cause of systemic instability. This might involve terminating a process that has become unresponsive, clearing temporary files, or resetting the application to a known state by restarting the session. By systematically killing hung processes before reattempting an operation, we avoid the accumulation of zombie instances that eventually exhaust system resources. Integrating these recovery steps ensures that our automation remains predictable, even when the underlying software exhibits intermittent behavior. Logging is another critical responsibility of an advanced exception block. When a block fails, we should capture the exact state of the environment before proceeding with any recovery attempt. This includes diagnostic snapshots, such as capturing screenshots or serializing the current values of critical variables, which are invaluable for post-mortem analysis. By outputting these details to an external log file or a dedicated monitoring queue, we move beyond simple error codes and towards readable audit trails. This diagnostic data allows us to identify patterns and failures, such as specific times of day or particular machine configurations that correlate with higher error rates, enabling us to refine our automation strategy based on empirical evidence. Once the cleanup and logging logic is complete, we must determine how the flow should proceed, which is where the configuration of the on-error behavior becomes paramount. The Go to Next Action option is suitable if we have successfully bypassed a non-critical failure and can continue the process from a point of stability. However, when dealing with transient faults like network spikes or temporary application locks, the repeat block command is often the superior choice. By repeating the block, we trigger the execution from the very first step of our grouped sequence, effectively providing a retry mechanism that includes all the necessary setup steps. This approach ensures that if a prerequisite like a database connection is lost, it is reestablished before the sensitive operations are attempted again. Implementing this level of control requires careful consideration of how exceptions propagate through the stack. If we have nested blocks, an error within an inner block can be caught locally or allowed to bubble up to a more generic, higher-level container that acts as a catch-all for unexpected scenarios. We should always prefer specific recovery paths for known failure points, leaving the wider blocks to catch unhandled platform exceptions. This layering of error handling transforms a brittle script into a hardened application capable of managing the volatility inherent in interacting with legacy user interfaces. Strategic use of block-level patterns directly impacts the reliability metrics of our automation, reducing the need for human intervention. I look forward to discussing how these blocks integrate into our larger workflows in the next segment. Welcome back. In this session, we will examine the architectural necessity of breaking down complex desktop flows into modular subflows to achieve true system resiliency. Software engineering principles teach us that complexity is the enemy of reliability, and robotic process automation is no exception to this rule. When we treat a desktop flow as a single, linear block of actions, we inadvertently create a fragile system where a failure in one isolated component cascades into a total process breakdown. By decomposing your automation into distinct, functional units called subflows, you transform a monolithic script into a suite of manageable services. Think of these subflows as discrete methods in a well-factored codebase, where each piece has a single, well-defined responsibility. This approach allows you to isolate the initialization logic, such as environment checks or credential retrieval, from the core business processing logic that interacts with target applications. When these components are decoupled, troubleshooting becomes a surgical operation rather than a vague investigation into thousands of lines of execution. One of the primary advantages of this modular design is the ability to maintain a clean state during execution and, crucially, during failure recovery. Imagine a scenario where your flow is interacting with a legacy Windows application that occasionally hangs or suffers from memory leaks. If you embed your cleanup logic directly into your main narrative flow, it becomes duplicated, difficult to update, and prone to oversight. Instead, by dedicating a specific subflow to handle application cleanup, you centralize the instructions for closing hanging processes, clearing temporary directories, and resetting the local workstation environment. When an error occurs elsewhere in your system, the main flow can simply invoke this recovery subflow to return the machine to a consistent baseline state before attempting a retry. This consistency is the foundation of unattended automation, where human intervention is not available to clear a stuck user interface or reboot a system. Managing operational context in a modular system requires a disciplined approach to variable scoping and data passing. While Power Automate Desktop provides global variables that are accessible across your entire flow, relying too heavily on them can obscure data flow and make your processes difficult to reason about. Instead, aim to treat your subflows as functions that accept inputs and produce clear outputs, keeping the global footprint to only essential configuration settings or shared session identifiers. For example, if your login subflow requires a set of credentials and returns a success flag or user ID, structure it to accept these inputs explicitly and pass back the result to the caller. This encapsulation ensures that if you ever need to change the implementation details of how that login occurs, perhaps moving from a localized file to a secure vault system, you modify only the internals of the subflow without breaking the contracts established with other parts of your automation. Dynamic invocation is another powerful technique when working with subflows, allowing you to build highly flexible execution paths. By utilizing logic loops or conditional triggers in your main flow, you can decide at runtime which subflow needs to run based on the specific requirements of the data being processed. If you are handling invoices with varying structures, your main flow might parse the initial data and then dynamically call an extraction subflow specific to the vendor type identified. This keeps your main business process logic uncluttered and focused on orchestrating high-level activities rather than detailing the minutiae of every possible variation in the application interface. The robustness of your automation increases proportionally to how well you can isolate these variations into their own subflows, shielded from the primary execution thread. Resiliency is ultimately defined by how an automation behaves when it encounters an exception, and a modular architecture pays dividends here. By wrapping your calls to these functional subflows in structured error handling blocks, you create a safety net that catches failures before they escalate to an unrecoverable state. When an action fails, your error handling routine should immediately hand off control to a standardized recovery subflow, which can perform forensic tasks such as taking a screenshot of the corrupted UI or logging the specific state of the application window. Because this recovery mechanism is a dedicated, reusable subflow, you only have to maintain those failure handling steps in one place, ensuring that your entire suite of automations benefits from the same rigorous error recovery logic. This architectural shift from linear scripts to modular services is what distinguishes a professional-grade RPA solution from a fragile, proof-of-concept prototype. See you in the next lesson. Hello, and welcome back. In this session, we will examine the debugging capabilities provided within the Power Automate Desktop Designer to help you isolate and resolve logical issues effectively. When we build desktop flows, the transition from successful logic to unexpected behavior is often subtle and stems from nuanced interactions with the underlying UI elements. The Power Automate Desktop Designer provides a robust set of tools specifically engineered to inspect the state of your automation at runtime, ensuring that you are not simply guessing where a sequence of actions might be failing. The starting point for any serious debugging session is the strategic placement of breakpoints. By clicking in the margin next to an action, you effectively instruct the engine to halt execution precisely at that line, providing you with a snapshot of the environment exactly as it exists before the action executes. This is your most vital instrument, as it prevents the flow from racing past the point of failure. allowing you to establish a stable environment for further investigation without the need to modify your production logic just to test a hypothesis. Once a flow is paused at a breakpoint, you should transition into granular execution control to observe how individual actions manipulate your data and the UI. Using the step into command allows you to follow the execution flow meticulously, especially when dealing with subflows or custom functions where the logic might be hidden from the main canvas view. Alternatively, the step over control is indispensable when you are confident in the behavior of a particular sub-action block and wish to bypass its internal complexity to focus on the subsequent steps in your main flow. As you navigate through these steps, the variable inspection panel becomes your primary source of truth. It displays the current values of all defined variables in real time, enabling you to detect when a particular calculation or extraction operation produces an unexpected result that deviates from your original design requirements. Beyond inspection, the power to modify variable values on the fly during a paused state is a technique that significantly accelerates the diagnostic process. You can manually override a variable's value to simulate a specific condition or to bypass a known problematic state, allowing you to continue testing the subsequent paths of your flow without having to restart the entire sequence. This interactive capability, combined with the comprehensive error logs provided by the designer, forms the backbone of a disciplined debugging workflow. When an error occurs, the red visual indicators provide an immediate alert, but the deeper value lies in interpreting the stack trace and the specific error codes returned by the runtime engine. By clicking into these logs, you can identify whether the failure is a transient issue, such as a timeout waiting for a UI element, or a more permanent flaw in your data transformation logic, allowing you to isolate and resolve even the most deeply nested problems efficiently. Effective debugging is not merely about identifying the point of failure, but about maintaining a logical mental model of how your flow interacts with the Windows environment under different conditions. As you work through these tools, remember that each pause provides a window into the current application state, which is often more informative than any theoretical analysis. By observing the interplay between your variables and the active UI window, you can determine if the selectors you have defined remain stable or if they need to be calibrated to account for dynamic elements. Consistency in using breakpoints and stepping through logic will eventually strip away the ambiguity of your automations, replacing frustration with a deep understanding of your code's behavior. Relying on these integrated utilities is a professional standard that differentiates a competent developer from someone who simply hopes for the best during execution. I will see you in the next lecture. Welcome back to our exploration of robust enterprise automation design. In this lesson, we will focus on the architectural necessity of standardized error logging and diagnostic frameworks. When we automate complex business processes, the happy path is rarely the main challenge we face as developers. Real-world systems are inherently volatile, prone to network latency, unexpected UI changes, or data validation failures that interrupt execution. A sophisticated enterprise automation does not merely fail, it communicates its failure states with enough precision to make the resolution trivial for support personnel. By implementing a standardized logging framework, you shift the burden of proof away from the developer and toward a data-driven model, where diagnostic telemetry speaks for itself. This practice is essential for maintaining high availability in unattended scenarios where human oversight is minimal. To build a truly resilient system, you must capture critical context at the moment of an exception, starting with the environment variables. Essential metadata should include high-resolution timestamps, the specific machine name executing the task, the user context under which the process runs, and a descriptive error message retrieved directly from the flow exception object. We often overlook the power of visual evidence, but including a base 64 encoded screenshot is arguably the most effective way to understand a UI-based failure. By converting the desktop image into a binary string within the flow, you enable the automation to attach a visual snapshot of the screen to your log record. This effectively gives support teams a window into the exact state the desktop was in when the logic stopped. The choice of storage for this telemetry depends entirely on your compliance requirements and the existing infrastructure of your organization. For smaller local implementations, appending error data to a flat text file or a specialized CSV is an acceptable baseline, though these are often difficult to aggregate across machine fleets. A more mature approach involves writing these entries to the Windows Event Viewer, which allows infrastructure teams to ingest logs into centralized tools like Azure Monitor or System Center Operations Manager. However, for a fully cloud-native Power Automate strategy, the most scalable path involves writing telemetry directly into a dedicated Dataverse table. By creating custom entities to house these logs, you gain the ability to use Power BI to visualize error trends over time across different geographical zones or departments. Designing these frameworks requires a consistent, modular approach so that logging logic does not clutter your primary business processes. Rather than scattering write-to-log actions throughout every subflow, encapsulate this functionality into a reusable subflow that accepts parameters. Your logging subflow should receive the current exception object, the failing action name, and a status code. Then handle the heavy lifting of formatting and dispatching the data to your storage provider. This decoupling allows you to update your logging infrastructure, such as switching from local text logs to an API call for a cloud logger, without touching the core business logic. It reinforces the principle of having a single source of truth for all diagnostic data within your solution. Finally, prioritize actionability in every piece of telemetry you collect to ensure that operational downtime remains low. Too many developers confuse verbose logging with useful logging, resulting in log files filled with redundant information that obscures the actual root cause. Every log entry should answer questions about the specific state of the variables at the time of the error and the path the execution took to arrive there. If a support analyst cannot deduce the required fix within minutes of reviewing your log, the framework is likely insufficient. By refining your diagnostic payloads, you turn the automation process into a self-documenting system that significantly matures your organization's RPA posture. I look forward to discussing how these logging frameworks integrate into your final automation deployments. Welcome to this chapter on Cloudflow architecture, where we will examine how cloud-based orchestration enables robust robotic process automation. When we discuss the architecture of Power Automate, it is helpful to view Cloudflows as the sophisticated central nervous system of your automation ecosystem. While desktop flows handle the mechanical interaction with legacy applications and local user interfaces, Cloudflows operate in the background as the primary orchestrators. A well-designed Cloudflow abstracts the complexity of timing, external connectivity, and business logic from the fragile, screen-based world of RPA. By decoupling the trigger and the orchestration from the actual execution on a local machine, we gain the ability to scale our automation across multiple environments and runtime targets. This architectural separation is not merely a design preference. It is a prerequisite for building sustainable, maintainable, and enterprise-grade robotic solutions that can withstand the inevitable variances of production environments. The Cloudflow Designer provides a visual canvas that acts as the entry point for your integration logic, encompassing a wide array of triggers and actions. We categorize triggers into three primary buckets: automated, scheduled, and instant. Automated triggers react to events in your ecosystem, such as a row being added to a SQL database, an email arriving in a specific Outlook folder, or an API call reaching a Power Automate endpoint. Scheduled triggers, conversely, operate on precise crons or time-based intervals, which are essential for batch processing tasks that do not rely on external event spontaneity. Instant cloud flows provide a bridge for human-in-the-loop scenarios, allowing users to trigger complex automated workflows via a manual button press from a mobile device or a browser window. Mastering these entry points allows you to build a proactive system that responds to business events rather than one that waits for human intervention. Variables within the cloud environment behave differently than their desktop counterparts, primarily because they are scoped according to the flow's execution context. In cloud flows, you typically handle variables through initialization and subsequent manipulation actions, which allow you to maintain state throughout the lifecycle of a single execution thread. These variables hold data that travels between connectors, acting as the glue that binds disparate APIs. When architecting your flows, you must remain cognizant of the data throughput and the limitations of these variables, particularly when dealing with large payloads or arrays. Well-structured data handling at the cloud level ensures that when you eventually initiate a desktop flow, the information passed down is already sanitized, validated, and ready for use. This preemptive data preparation minimizes the overhead on the desktop machine and reduces the likelihood of unhandled exceptions occurring during the UI automation sequence. Designing for the cloud requires a mindset that prioritizes asynchronous execution and resilience against network latency or API rate limits. Because a cloud flow sits at the top of the hierarchy, it must effectively manage the handoff to the desktop runtime environments. You should think of your cloud flow as a state machine that monitors the status of downstream processes. By leveraging error handling blocks at the cloud level, you can implement retry policies or alternative routing paths if a desktop flow fails to trigger or encounters an unexpected machine-side issue. This level of orchestration ensures that your automation platform is not merely a collection of scripts, but a managed service capable of delivering consistent business outcomes regardless of where the individual components execute. Proper architecture here allows you to pivot between different automation patterns as your business requirements evolve over time. See you in the next lecture. Welcome back. In this session, we will explore the mechanisms required to bridge the gap between cloud-based orchestration and local desktop automation. The primary interface for this integration is the cloud-native action titled Run a Flow built with Power Automate Desktop. When you drop this action into your cloud flow, you are effectively signaling the Power Automate service to initiate a handshake with a designated agent installed on your machine. This connection relies heavily on the machine registration process, which binds a local device to your environment within the broader Power Platform ecosystem. By abstracting the complexities of networking, this action allows the cloud to treat your local machine as an execution node. You must ensure that your local agent is properly signed in and that the machine appears as valid within the cloud portal. Without this registration, the cloud dispatcher cannot locate or communicate with your local automation runtime. Configuring the connection often involves choosing between direct machine connectivity or the use of on-premises data gateways. Machine connectivity is generally preferred for modern infrastructure as it simplifies the network footprint and leverages native cloud agents that communicate securely via outbound connections. However, in legacy environments or strictly segmented networks, an on-premises data gateway acts as a secure bridge, relaying the instructions from the cloud to your local desktop controller. When setting up these profiles, you are defining the identity under which the desktop flow will execute. The credential management here is paramount, as the runtime requires sufficiently privileged access to the local machine's OS and internal applications. Misconfiguration at this layer is a frequent cause of execution failures, typically manifesting as authentication timeouts or authorization errors during the initial handoff. Choosing the correct runtime mode is a critical design decision that dictates how the desktop flow interacts with the Windows session layer. Running a flow in attended mode implies that the automation shares an active user session, which is optimal for tasks requiring human interaction or real-time verification. Because the user is present, they can observe the actions on the screen and potentially intervene if an unexpected state occurs. Conversely, unattended mode is designed for complete process isolation, where the runtime instantiates its own dedicated session. This is the hallmark of enterprise-grade RPA, as it allows processes to run in the background without needing a user logged into the console. The environment treats these unattended runs as autonomous entities, ensuring that UI interactions are performed within a protected context that does not interfere with other active desktop tasks. When transitioning to unattended execution, you must account for the overhead of session creation, as the runtime must clear existing states or establish a fresh environment. This often necessitates that your desktop flows are built with absolute stability and comprehensive exception handling, as there is no human operator to click past dialog boxes or resolve unexpected application prompts. You should architect your workflows to be headless wherever possible, minimizing reliance on visual components that might vary across different resolution settings or session types. It is your responsibility as a developer to ensure that the machine's local configuration matches the requirements of the runtime profile chosen in the Cloudflow. By aligning your execution strategy with the specific needs of your business logic, you create an automation framework that is both secure and resilient. See you in the next lecture. Welcome back. And today we turn our attention to the mechanics of managing desktop flow run queues within the Power Automate architecture. This is a critical component for anyone building scalable, unattended automation solutions. When we initiate a desktop flow from a cloud flow, we are not necessarily triggering an immediate execution on a target machine. Instead, we are submitting a request into an orchestration layer that manages the lifecycle of that job until a machine becomes available. Understanding this queuing behavior is fundamental, especially when we start distributing automation workloads across machine groups rather than individual nodes. The cloud service acts as a broker, evaluating the availability of machines within a specified group and assigning pending flows based on a first-in, first-out sequence modified by priority levels. If all machines in your target group are currently busy, the request enters a pending state within the queue. This is where your design decisions regarding concurrency and resource allocation begin to impact the overall throughput of your automation platform. Prioritization is the primary lever you have for controlling the flow of work during peak demand periods. When you trigger a desktop flow, you can explicitly set the run priority to high, normal, or low within the Cloudflow action. The queue service processes these requests by favoring high priority jobs over others, even if those high priority flows arrive later than existing low priority items. However, relying too heavily on high priority can lead to resource starvation for lower priority yet essential business processes. You should treat priority as a tool for managing exceptions and urgent business requirements rather than a standard operational setting for all jobs. Effectively, the runtime infrastructure attempts to drain the queue by cycling through available machines and matching them with the most urgent pending job that matches the required machine capabilities. Concurrency control is a vital aspect of your infrastructure design, particularly when you have multiple flows competing for the same set of machines. Within the Power Automate platform, you can configure machine groups to handle multiple flows concurrently, provided the host machines can support the processing overhead. If you enable concurrency, you must be careful to avoid oversubscribing the CPU or memory resources of your virtual or physical machines. If a machine reaches its capacity, any additional flows assigned to it will remain in the queue until the current run terminates, which is essentially the serialization mechanism in action. You must monitor these queues to detect when backlogs begin to form, as a growing queue is often an indicator that your machine-to-workload ratio is no longer balanced. To prevent deadlocks and unexpected failures, we must also consider the cloud action timeout boundaries carefully. Each call to run a desktop flow has an associated timeout, and if the flow remains in the queue for too long without being picked up by a machine, the Cloudflow action will time out and potentially return an error. You need to align your timeout configurations with your business requirements for execution latency. Sometimes, it is better to fail gracefully and alert an administrator than to allow a process to linger in the queue indefinitely, consuming memory and waiting for a machine that might never become free. Keep in mind that deadlocks can occur if your logic creates complex dependencies where one flow is waiting for a machine that is pinned by another process that is itself waiting for the first process to finish. Effective orchestration of these flows requires a deep understanding of your infrastructure capacity. You should track the number of successful runs, the time spent in the queue, and the total execution time for your automated tasks. By analyzing these metrics, you can identify patterns in your workload that inform decisions on when to scale your machine groups up or down. A well-designed automation pipeline does not simply execute tasks. It manages intent and resources to ensure that the most important business outcomes are met within the constraints of your current runtime environment. As you move toward more complex architectures, consider how these queuing mechanics serve as the backbone for stable and predictable digital worker performance. See you in the next lecture. Welcome back. Today we examine the technical strategies required to manage infrastructure-level instability when your cloud flows depend on on-premises gateway connectivity. When we integrate cloud flows with on-premises desktop flows, we naturally introduce a dependency on the gateway service. Unlike local code, which executes within a controlled environment, the gateway introduces network latency, potential authentication timeouts, and physical machine availability constraints. A robust RPA architecture cannot assume that every request to the Power Automate gateway will succeed. We must anticipate scenarios where the gateway is unreachable, the machine is offline, or the specific session remains stuck. By failing to account for these environmental variables, we create fragile automations that require constant manual intervention. Our goal is to shift from reactive troubleshooting to a proactive design that treats gateway failures as expected runtime events rather than catastrophic system shocks. The primary mechanism for managing these failures lies in the configure run after property within the Power Automate Cloud Designer. By default, an action only executes if its predecessor succeeds, but this is insufficient for handling infrastructure errors. You can modify this setting to trigger specific remedial actions if the previous step has failed, timed out, or skipped. When a desktop flow action fails due to a connectivity issue, the output includes specific error codes and status properties that we can inspect. Instead of allowing the flow to terminate, we use these diagnostic outputs to steer the execution towards a decision-making layer. This might involve an immediate retry mechanism, which is often effective for transient network blips that resolve themselves within a few seconds. Scaling beyond simple retries, we can design logic to redirect tasks to alternative machine groups if the primary gateway remains unresponsive. If a gateway timeout is detected, the Cloudflow can dynamically route the serialized work item to a secondary machine capable of performing identical tasks. This pattern requires a well-structured dependency injection approach where the machine identifier is treated as a configuration variable rather than a hard-coded value. Simultaneously, we must ensure visibility by alerting administrator groups through integrated communication channels like Microsoft Teams or Outlook. By parsing the error object returned by the desktop flow action, we can compose meaningful messages that include the error code, the machine name, and the timestamps. Failure to notify stakeholders effectively is often the reason why small gateway connectivity issues snowball into significant business downtime. Reliability also requires consistent auditing, which we achieve by pushing failure states into an external repository, such as in SQL database or a dedicated Dataverse table. Every time a gateway failure occurs, the Cloudflow should log the unique run identifier and the specific nature of the hardware or network error. This logging pattern provides the raw data needed for long-term health monitoring and capacity planning for your RPA infrastructure. If we observe a pattern of recurring connectivity issues on specific machines, the logs will provide the evidence necessary to justify hardware upgrades or network configuration changes. Treating logs as first-class citizens in your automation design makes the difference between an ephemeral script and a production-grade enterprise service. By following this disciplined approach, you ensure that your automation processes remain resilient even when the underlying infrastructure fails. See you in the next session. Welcome back. In this lecture, we will integrate cloud-based triggers with local desktop execution to build robust, end-to-end orchestration pipelines. Enterprise-grade automation rarely lives exclusively in the cloud or strictly on the desktop. When we architect a system meant to handle real-world invoices, we are designing a bridge between modern SaaS capabilities and legacy infrastructure. Imagine a scenario where an invoice arrives as an email attachment. The Cloudflow serves as the initial gatekeeper. It orchestrates the flow by extracting metadata, such as vendor names, net amounts, and invoice dates, using AI-driven connectors or standard parsing actions. Once this data is sanitized and structured, it acts as a payload for the Power Automate desktop flow. This handoff is a critical juncture where we must ensure data integrity before the desktop engine takes control to drive an ERP system that may lack an API. When moving data from the cloud context into the desktop domain, you must treat your input arguments with great care. These inputs are the primary interface for your desktop flow, and they should be defined as clear, distinct variables within your Power Automate desktop workflow. By strictly defining these parameters, you minimize the risk of type mismatch errors when the legacy ERP system attempts to read the data. Once the desktop flow executes, it interacts with the UI elements of the ERP application, processes the data, and concludes by committing a transaction. The receipt of an order number, the success signal of your transaction, must then be passed back to the Cloudflow to finalize the loop. This return value is essentially the output signal that triggers the downstream actions in your orchestration. Designing this communication requires a sound understanding of how Cloudflows wait for desktop responses. You are not just firing a request and hoping for a signal. You are managing a synchronous dependency. If your desktop flow takes several minutes to process an entry, the cloud flow must remain in a state that acknowledges this duration without timing out. This is where the configuration of your run settings becomes paramount. By utilizing the run of flow built with Power Automate for desktop action, you essentially establish a session. You should structure your cloud flow to interpret the output object returned by this action, checking for status codes or specific key value pairs before proceeding to the final update step. Once the order number is safely back in the cloud, you must update your system of record, such as Dataverse, to reflect the completed state of the invoice. This architectural pattern ensures that your cloud-side database serves as the single source of truth for the entire lifecycle, regardless of where the heavy lifting occurred. Alongside the database update, you should implement notification logic, perhaps sending a confirmation email or a Teams notification to the relevant stakeholders. This ensures that the automation is not just a silent background process, but a transparent part of the enterprise workflow. Designing this requires careful attention to the success and failure branches of your cloud flow to ensure that failures in the desktop layer are caught, logged, and reported rather than vanishing into a void. Performance and reliability in these multi-tier architectures depend heavily on how you manage your resources. You are effectively connecting two distinct environments that do not share the same uptime characteristics or processing limitations. When designing for the enterprise, you must account for the latency inherent in passing data through the on-premises data gateway. To optimize this, minimize the amount of data transferred back and forth by passing only necessary primitives rather than large objects. Additionally, ensure that your desktop flows are built to run headlessly whenever possible to conserve system memory and prioritize execution speed. Reliability increases when you decouple the reception of the email from the actual processing, perhaps by queuing the requests in Dataverse first, allowing the desktop flows to consume them at a sustainable rate. Security, of course, remains non-negotiable throughout this chain. When cloud flows pass sensitive invoice data to a machine group, that data is encrypted during transit through the gateway. However, you must also consider the principle of least privilege regarding the credentials used to access the desktop applications. Use credential manager configurations appropriately so that the automation runtime, not the developer's identity, carries the permission necessary to interact with the ERP. By encapsulating these operations within managed solutions, you further harden the deployment by promoting only validated, versioned versions of your orchestrations to your production environment. Every interaction between the cloud and the desktop must be logged, ideally with enough metadata to reconstruct the state of the invoice at any point in the pipeline if verification is required during an audit. See you in the next lecture. Welcome back. Today we will examine the distinction between standard and premium connectors and how to effectively deploy them within your automation orchestration. In the Power Automate ecosystem, the efficacy of an automation often comes down to the quality of the integration points you select. Microsoft provides an expansive library of pre-built connectors that act as intermediaries between your business logic and external systems. These connectors are fundamentally categorized as either standard or premium, a distinction that carries significant weight regarding both technical capability and financial expenditure. Standard connectors are typically those that interact with services that are widely considered commoditized or native to the Microsoft 365 environment, such as SharePoint, OneDrive, or Outlook. Because these services are bundled into many foundational licensing tiers, they require no additional per-user pricing for their utilization. When you build a flow that triggers on a file upload in OneDrive or sends an email via Office 365, you are using these standard capabilities, which provide a reliable and supported interface without increasing your monthly cloud infrastructure costs. The landscape shifts noticeably when we discuss premium connectors, which are required for systems that fall outside of the basic Microsoft 365 service set. These connectors grant you access to enterprise-grade resources such as SQL Server, various Azure services like Key Vault, or external third-party software as a service platforms. The use of these connectors necessitates a specific Power Apps or Power Automate per user or per flow license, as Microsoft reserves these more resource-intensive or specialized integrations for higher-tier subscription levels. When designing an orchestration pipeline, it is crucial to recognize that the requirement for a premium license is not merely a bureaucratic hurdle, but often reflects the complexity of the data source being interfaced. You must perform a rigorous cost-benefit analysis before deciding to implement a premium connector, ensuring that the business value of automating data interaction with a specific database justifies the incremental licensing expense incurred by the project. From a technical perspective, the goal should always be to prefer API-based interaction over UI-based automation whenever possible. UI automation, while powerful for legacy applications that lack any exposure to modern interfaces, is inherently brittle due to its dependence on the visual state of the application being manipulated. When you use a connector, you are essentially replacing the need for screen scraping or pixel-based clicking with a formal request addressed directly to the backend of the target system. This shift reduces the impact of UI changes, as the underlying API contract remains stable even if the vendor updates their web interface or desktop client application. By utilizing standard and premium connectors, you move your integration logic into a declarative space that is easier to maintain, faster to execute, and significantly more resilient to environmental shifts in your enterprise architecture. When implementing these connectors within your cloud flows, you need to be mindful of the authentication context and the scope of access being granted. Many premium connectors, such as those for SQL Server, require specific configuration regarding connectivity, often necessitating the use of an on-premises data gateway if the resource resides within a secured internal network. This adds a layer of infrastructure management that you must account for during your solution planning phase, as the uptime of your orchestration will be directly tethered to the availability of that gateway. Furthermore, when working with services like Azure Key Vault via a premium connector, you are introducing advanced security patterns into your orchestration flow. These patterns allow you to manage sensitive credentials outside of the flow definition itself, which is a best practice for maintaining a secure and professional-grade environment that adheres to modern data governance standards. As you build your integration strategy, always prioritize the use of standard connectors to keep costs low and minimize the need for specialized licensing for end users. Only pivot to premium connectors when the necessary functionality, such as direct database write operations or integration with proprietary business applications, demands it. It is also worth noting that once a flow contains a single premium connector, the entire flow is considered premium and requires elevated licensing for anyone running it. Keeping your orchestration logic segmented can sometimes help in optimizing these costs. For instance, you might use a child flow architecture to isolate premium operations. By understanding these functional and licensing implications, you will be well equipped to design robust, cost-effective automation solutions that rely on stable API communication rather than fragile UI interactions. See you in our next exploration of custom connectors and integration patterns. Welcome back to our journey toward mastering the PL-500 certification, where we turn manual bottlenecks into automated success. Today, we begin our deep dive into the architecture of custom connectors. In this chapter, we will master the technical landscape of building and deploying custom connectors to bridge the gap between Power Automate and proprietary REST APIs. By the end, you'll be able to securely define authentication, map complex payloads, and ensure your custom services integrate seamlessly into your production automation workflows. When we interact with systems lacking a pre-built connector, the custom connector becomes our primary interface for extending the Power Automate ecosystem. You begin this process by defining the host, typically the base URL of your API service, and selecting the appropriate security protocol. Whether you are implementing API key, basic authentication, or the more robust OAuth 2.0 flow, your primary concern is maintaining the integrity of credentials. OAuth 2.0, for instance, requires registering your application within the identity provider to acquire a client ID and secret, which the connector then uses to acquire access tokens dynamically. This abstraction is significant because it allows the flow author to focus purely on the business logic rather than the low-level concerns of maintaining authorization headers or managing token expiration windows. Once the connectivity layer is established, you move to API operation definitions. While you can manually define every path and method, the most efficient approach is to import an open API or Swagger specification file. This process automatically generates the structural definition of your endpoints, including path parameters, query strings, and expected response schemas. After the import, your responsibility shifts to refining the metadata. You should verify that input fields are correctly typed and mapped. as this greatly improves the developer experience for anyone consuming your connector in a Cloudflow. Providing clear titles and descriptions for every parameter ensures that the generated action cards are self-documenting and intuitive for the end user. Data transformation represents the most common hurdle when interfacing with non-standard APIs. Frequently, a legacy API will return a payload structure that does not align neatly with the data objects required by your downstream Cloudflow. To mitigate this, we rely on policy templates to manipulate incoming or outgoing data. You might use the setHeader policy to inject dynamic values required by the backend, or perhaps the route request policy to redirect calls based on specific environmental variables. These transformations occur at the connector level, acting as a middleware layer that sanitizes and reshapes traffic before it ever touches your flow logic. By investing time here, you significantly reduce the amount of complex parsing actions required within the Power Automate Designer. Testing a custom connector follows a rigorous lifecycle that begins within the builder interface itself. Before pushing a connector to a production solution, you must utilize the testing capability to perform a dry run of your API operations. This is the stage where you identify issues with JSON serialization or missing required headers that might not manifest until the flow is triggered by an actual event. Keep in mind that when deploying, the connector acts as a component within a Power Platform solution. This means lifecycle management, environment variables, and connection references must be handled with the same care as Cloudflow's or desktop automation scripts. A well-constructed custom connector is not just a point of integration. It is a reusable asset that matures alongside your automation portfolio. See you in the next lecture. Hello. We are going to explore how to transition from basic record manipulation to implementing deep transactional integrations with Microsoft Dataverse. When we approach Dataverse as more than just a simple database, it becomes the backbone of our enterprise automation strategy. By utilizing the native Dataverse connector, we can perform CRUD operations while maintaining the integrity of our relational data models. This means we move beyond simple row insertion and start leveraging complex OData query expressions to fetch highly specific filtered datasets. Using the filter rows field in the list rows action allows us to minimize data transfer, which is a critical consideration when designing performant cloud flows that interact with large enterprise systems. You should treat the OData query as your primary tool for data retrieval, as it pushes the filtering logic to the server side rather than pulling massive lists into your flow memory. Transactional consistency is arguably the most vital concept to master when dealing with multiple related records. If you're updating an account record and simultaneously creating multiple related contact rows, you must ensure that these operations succeed or fail as a single unit. Dataverse supports the execution of batch requests within a transaction via the use of change sets, which prevents half-finished records from cluttering your environment. Without transactional consistency, your automation risks entering an inconsistent state should a network interruption occur mid-flow. Always consider the atomicity of your integration logic when you are dealing with business-critical data that resides across multiple tables. Optimistic concurrency control is another important mechanism that helps us avoid data corruption in multi-user automation environments. By using the if-match header with an e-tag, you can force the Dataverse connector to check if a record has been modified by another process since you last retrieved it. If you attempt an update on a stale record, the system will reject the request, allowing your flow to handle the conflict gracefully rather than overriding valid data. This is particularly relevant in unattended automation scenarios where multiple agents might be competing for the same resource. You should incorporate exception handling blocks to manage these specific concurrency errors and implement retry logic when necessary. Handling relational lookups and polymorphic relationships requires a disciplined approach to schema awareness. When you write a value to a lookup field, you are responsible for providing the globally unique identifier or the relative path string, which requires you to understand the underlying GUID structure of your tables. Polymorphic relationships add another layer of complexity, as you must correctly define the table type in your lookup reference to ensure the transaction is correctly routed. Take the time to inspect your system tables via the Power Apps portal before designing your automation steps. A clear understanding of your data schema will save you from common runtime errors associated with invalid references or missing keys when working with high-volume enterprise automations. Change tracking is yet another feature that you can leverage to optimize your integration patterns, especially when you are performing delta-based synchronizations. Instead of processing entire datasets on every flow run, you can query only the records that have changed since your last execution. This significantly reduces the overhead on the Dataverse platform and minimizes the latency of your automated processes. By implementing this pattern, you transform your cloud flow from a simple script into a robust, state-aware integration engine. As we continue, keep in mind that Dataverse is intended to be the single source of truth for your state management, acting as a secure and centralized log for all enterprise activity. I will see you in the next lecture. Welcome back. In this session, we will explore how AI Builder transforms unstructured data into actionable intelligence within your Power Automate workflows. Integrating cognitive services into automation allows us to move beyond rigid, rule-based processes towards systems that can interpret human input. Text recognition, or optical character recognition, acts as our bridge between the physical and digital worlds by extracting printed or handwritten text from images. When you employ these pre-built AI models, you stop manually typing data from receipts or forms and instead rely on an automated pipeline that feeds directly into your business processes. It is vital to remember that these models effectively mitigate the inaccuracies introduced by manual human entry. Once the text is digitized, we can chain these operations together to handle higher-order tasks like routing and classification. Designing these workflows requires a clear understanding of the confidence scores these models return to ensure you are not acting on unreliable data. Once we have processed raw text, we shift our attention toward understanding the sentiment and intent behind the communication. Sentiment analysis offers a numerical representation of the emotion conveyed in incoming emails or support tickets, allowing your automation to prioritize urgent or dissatisfied customers automatically. Meanwhile, entity extraction and category classification automate the administrative burden of sorting incoming data by identifying names, locations, or specific categories like billing versus technical support. Language detection completes this suite by ensuring that your multi-regional workflows interpret inputs correctly regardless of the origin. By deploying these models, you shift the architecture from simple automation to a cognitive-aware ecosystem that reduces operational latency. These components behave like discrete services in a larger architecture, which is why we must treat them as replaceable parts of our orchestration logic. Prediction models represent a distinct shift in strategy, moving from reactive automation to proactive business intelligence. Unlike recognition models that interpret current data, prediction models rely on historical datasets to forecast future outcomes like customer churn or lead conversion. Implementing these requires a disciplined approach to data hygiene, as the quality of your training data directly influences the model's predictive power. Within your cloud flows, you pass parameters to these models and receive a result that can trigger conditional logic or enterprise-wide notifications. You are essentially building a feedback loop where your RPA processes gather data, store it in Dataverse, and let the AI model suggest the next best action. This approach is highly effective for environments that need to optimize resource allocation without human intervention. Complexity grows when you start layering these disparate AI capabilities into a single end-to-end process. You might encounter a scenario where an image is scanned, processed by the text recognition model, and then passed through an entity extraction model to determine its category before being routed. Each step introduces a dependency on the underlying AI service, which necessitates robust error handling to manage potential transient failures or API timeouts. By maintaining a modular design, you ensure that upgrading or changing a specific AI model does not break the entire workflow. The integration of AI Builder into your automation suite is not merely a feature addition. It is an architectural decision to embrace cognitive computing. By leveraging these tools, you're equipping your bots with the eyes and ears required to handle the ambiguity of real-world business data. I will see you in the next lecture. Welcome back to our exploration of Power Automate. In this session, we examine advanced integration patterns and the critical security requirements necessary for professional-grade automation. Building resilient enterprise solutions requires more than just functional logic. It demands a robust architecture that secures data across hybrid boundaries. When we bridge the gap between cloud-based automated workflows and on-premises systems, we encounter the challenge of maintaining trust, identity, and integrity. Using custom APIs as a conduit between these environments is a common scenario, but it necessitates careful handling of authentication credentials. Service principals are the industry standard here, providing a way to authenticate against Azure resources without relying on individual user identities. By delegating access via specific application roles, we adhere to the principle of least privilege while ensuring our unattended bots remain functional even after personnel changes. It is essential to treat these credentials as first-class citizens within your deployment, storing them in dedicated key vaults rather than hard-coding them within your flow definitions. Data security at rest and in transit represents another pillar of our architectural design. When transmitting sensitive information between a cloud environment and an on-premises machine, payload encryption is non-negotiable. You should implement TLS-based communication channels, ensuring that your on-premises data gateway acts as a secure tunnel for incoming requests. Furthermore, adhering to enterprise data governance frameworks means that we must audit every step of the execution cycle. Dataverse serves as an excellent repository for these audit logs, allowing us to maintain a tamper-proof record of what data was accessed, modified, or transferred during a process run. By centralizing these logs, we satisfy compliance requirements while gaining the necessary visibility to troubleshoot discrepancies in complex multi-step orchestrations. Optimization of performance is just as critical as security when dealing with high-volume enterprise automation. Integrating with external APIs often exposes us to service provider limitations, frequently manifesting as throttling or rate-limiting responses. A naive implementation might simply fail once a limit is hit, but a mature developer employs an exponential back-off strategy to handle these occurrences gracefully. By systematically increasing the wait time between retry attempts, we minimize the impact of our traffic on the target system while preserving the uptime of our own processes. Additionally, we must remain mindful of payload sizes, as excessive data volume can lead to latency spikes and unnecessary consumption of bandwidth resources. Compressing information before transmission or opting to send pointers to cloud-hosted storage instead of raw datasets are effective techniques for maintaining high-performance throughput. We will now look at how cognitive services interact within these secure environments. When automating document processing or utilizing predictive intelligence, we often send data to external AI endpoints. It is imperative that these connections use secure token passing, ensuring that the identity of the invoking service is verified through OAuth flows before any processing occurs. These cognitive workloads should be designed as modular, discrete tasks that reside downstream from our primary orchestration logic. By keeping the AI-specific integration patterns isolated from the core business workflow, we simplify the maintenance of sensitive logic and make it easier to rotate authentication tokens without disrupting the entire chain of execution. This modularity ensures that our architectural design remains adaptable to changes in platform capabilities or security requirements over time. See you in the next lesson. Welcome back. In this lesson, we will begin our exploration of application lifecycle management within the context of Power Automate. We are going to master the structural movement of automation assets through the various stages of the software development lifecycle. Application lifecycle management is the holistic process by which we manage the software development process from inception to decommissioning. In the Power Platform ecosystem, this is primarily achieved through the implementation of solutions, which act as the fundamental container for all our robotic process automation components. When we build flows, we are not merely writing scripts. We are architecting software that must eventually exist in testing and production environments. By encapsulating our cloud flows, desktop flows, connection references, and environment variables into a single package, we ensure that the deployment process remains repeatable and predictable. Failing to utilize these containers effectively often leads to fragmented configurations that are impossible to maintain at scale. Therefore, thinking in terms of transportability from your very first development day is essentially a prerequisite for professional RPA maturity. The distinction between unmanaged and managed solutions is the most critical conceptual barrier to overcome in this domain. An unmanaged solution carries the full source data, which allows you to modify, add, or remove components directly from within the environment. This is inherently the state in which you perform your development work. It is functional, flexible, and entirely mutable. However, Once you export a solution as a managed package, you essentially lock the definition of those components in a read-only state for the target environment. This managed state is vital for production deployments because it prevents accidental modifications that could lead to system instability. Understanding that a managed solution cannot be directly edited forces a more professional approach where every change must flow through your defined source control and development pipeline. Managing dependencies is where many developers find the most friction when moving flows across environments. Within a solution, every component might have relationships with others, such as a cloud flow requiring a specific connection reference or an environment variable. If you attempt to export a solution that points to a configuration existing only in your development instance, the deployment will predictably fail in your destination environment. To solve this, always ensure that your connection references are defined as independent entities rather than hard-coded authenticated sessions. This allows the target environment to supply its own authentication token, thereby decoupling the logic from the specific user identity used during development. Maintaining this abstraction is essentially the same as practicing dependency injection in code, ensuring that your automation logic remains oblivious to the environment-specific infrastructure. The mechanism of solution layering further governs how our components coexist during the deployment process. When you deploy a managed solution over an existing base, Power Platform applies a layer that dictates precedence based on the order of installation. If you make a mistake and need to roll back, understanding these layers is what determines whether your cleanup operation will succeed or leave behind residual traces. Effective ALM also requires us to distinguish between updates, which overwrite components, and patches, which are meant for smaller, incremental changes to an existing solution. By utilizing proper versioning strategies, you gain the ability to conduct clean upgrades without impacting the end users who rely on your automation every single day. Achieving this level of control requires disciplined naming conventions and a rigorous testing protocol before any managed payload is moved to production. As we move forward, remember that the goal of these sophisticated packaging tools is to reduce the manual intervention required during administrative deployments. We want a world where deployment is a button press and a pipeline rather than a frantic exercise in manual configuration. This maturity allows you to focus on developing better automation logic rather than fixing broken environment connections. Our upcoming focus will be on the technical granularities of the specific components we have discussed today. Until we meet again for the next technical breakdown, take care. Welcome back. In this lecture, we will explore the mechanisms for decoupling environment-specific configurations from your automation logic using environment variables and connection references. When we construct automation assets, we often fall into the trap of hard-coding values directly into our flows. If you hard-code a file path like c:\users\admin\documents or a specific development URL, your automation becomes brittle and essentially tethered to a single environment. This creates significant friction when moving solutions from a development sandbox to a production environment, as you would otherwise be forced to manually edit every instance of those values. By utilizing environment variables, you move away from this static approach and instead store these configurations as dynamic parameters. Environment variables act as definitions within your Dataverse solution, allowing you to pass values at runtime without altering the flow itself. You can store these as simple text, or if you're dealing with sensitive configuration keys, you can leverage secret variables. For complex configurations involving multiple key value pairs or structured data, you can implement JSON-formatted variables to keep your settings organized while remaining easily accessible to your logic. This architectural decision fundamentally changes how you deploy, as it shifts the responsibility of configuration from the internal automation code to the environment management layer. Beyond variable management, we must address the identity and connectivity aspect of our automations, which brings us to the concept of connection references. In a standard workflow, a connector instance relates to a specific credential or user session, which is problematic when you promote a solution to production. If your flow relies on a specific connection created under your developer account, the production environment will fail because it lacks appropriate access permissions. Connection references solve this by providing an abstraction layer between the action in your flow and the actual authentication connection used to execute it. When you build your cloud flow or desktop flow, you select the connection reference rather than a physical connection. This allows the administrator to map the reference to a legitimate, production-ready account during deployment. Because the underlying flow logic only knows about the reference name, it remains agnostic of the specific credentials, ensuring that the transition between environments is seamless and secure. To implement this effectively, you must understand how these components interact within the Dataverse solution framework. When you add a desktop flow to a solution, you should proactively verify that any hard-coded strings or path dependencies are converted into environment variables. During your design phase, create these variables as independent components so they can be bundled inside the solution package. Remember that environment variables can be scoped either to the specific solution or the environment itself, allowing for fine-grained control over how configurations are inherited or overridden. When you bind connection references to your actions, ensure that you are using the supported triggers and actions that facilitate this binding, specifically ensuring that your desktop flow orchestration supports the indirect connection model. This approach minimizes the surface area for errors during the implementation phase and significantly reduces the manual overhead typically associated with environment migrations. It is a hallmark of mature RPA development to treat infrastructure and configuration as separate concerns from process logic. By mastering these techniques, you ensure that your automation assets are robust enough to handle the transition from development to production without brittle code refactoring. You are essentially creating a reusable template that relies on local environment context to execute correctly. This practice not only aids in compliance and security by limiting the exposure of sensitive credentials, but it also empowers administrators to manage deployments with confidence. As you prepare for your certification, focus on how these components enable portability and maintainability within the Power Platform. Relying on these native features is standard practice for enterprise-grade automation systems designed for longevity and scalability. You will find that these strategies are essential when building out complex, multi-environment automation landscapes. See you in the next lecture. Welcome back. In this session, we will examine the infrastructure requirements and management lifecycle of the on-premises data gateway. The on-premises data gateway acts as a secure bridge between your local network resources and the Power Platform cloud services. Without this component, the cloud service cannot reach internal data sources such as local SQL databases, file systems, or proprietary on-premises applications. When architecting your integration, you must understand that the gateway does not require inbound ports to be opened on your firewall. Instead, it relies on outbound communication, specifically using TCP ports 443, 5671, 5672, and 9350 through 9354, or potentially HTTPS depending on your specific configuration. This architecture is designed to uphold strict security standards, ensuring that data is encrypted while in transit and that the local environment remains protected from unauthorized external access. Before deployment, always verify that your host machine meets the hardware and software prerequisites, including the appropriate .NET Framework version and operating system compatibility. Management of these gateways occurs through the Power Platform Admin Center, which serves as the centralized interface for configuring cluster properties and permissions. When you scale your automation environment, you will find that a single gateway installation often becomes a single point of failure that hampers operational resilience. By creating a high availability cluster, you can group multiple gateway installations to provide load balancing and automatic redundancy for your unattended desktop flows. If one node in the cluster goes offline for maintenance or due to a hardware failure, the Power Platform service automatically routes the traffic to the remaining healthy nodes in the group. Proper maintenance should always include a regular patching cadence, as running an outdated version of the gateway software can lead to communication timeouts and degraded performance metrics that impact the overall execution stability of your automation solutions. Security is not just about the network boundary. It is also about the granular control of who can interact with the gateway service itself. You must define clear access roles, distinguishing between users who can simply consume the gateway for their flows and those who have administrative rights to modify the infrastructure or add new data sources. Within the Admin Center, you assign these permissions to individuals or groups, which is a critical step in a governance model that adheres to the principle of least privilege. If you encounter frequent gateway offline errors, your troubleshooting diagnostic process should begin with the inspection of the gateway logs located on the host server. These logs often reveal connectivity issues to the Azure Service Bus or provide hints about internal service authentication failures that might otherwise go unnoticed. Monitoring the health of your gateway cluster is a proactive task that ensures your unattended automations run without unnecessary human intervention. You should periodically review the available metadata and performance telemetry to identify potential bottlenecks in your local network throughput. Because the gateway process runs as a Windows service, ensure that the service account used for its execution has the necessary local privileges to perform the required operations without escalating security risks to the rest of the host infrastructure. If the service experiences recurring crashes, investigate resource contention on the physical server, as CPU or memory exhaustion often manifests as intermittent connection resets. Keeping the gateway environment healthy is essentially about maintaining the integrity of the signal path between your automation logic and your enterprise data, which is just as important as the code you write within your desktop flows. I will see you in the next lecture. Welcome back. In this lecture, we will explore the orchestration of machine infrastructure by configuring machine groups and managing their runtimes for scalable, unattended automation. To facilitate unattended robotic process automation at scale, Microsoft Power Automate requires a robust mechanism to manage the physical or virtual machines that execute your desktop flows. Rather than assigning a process to a single static machine, you should organize your resources into machine groups. A machine group acts as a logical container for multiple machines, enabling the cloud orchestration engine to distribute workloads effectively. When a flow is triggered to run unattended, the Power Automate service looks at the available capacity within the group and selects the optimal machine to handle the execution. This abstraction layer is vital because it separates your business logic from the underlying infrastructure, allowing you to scale up or down without modifying your Cloudflow definitions. Managing multiple machines simultaneously necessitates a centralized approach to software lifecycle management, particularly for the Power Automate desktop runtime engine. The orchestrator allows you to review the health status of every registered machine, identifying those that may have lost connectivity or are experiencing registration conflicts. When you deploy updates to the desktop runtime software, you must ensure consistency across your machine pool to prevent execution failures caused by version mismatches. By grouping machines, you gain the ability to monitor the aggregate health and performance of your RPA fleet directly within the Power Platform Admin Center. These administrative tools provide the visibility required to troubleshoot connectivity issues, often caused by certificate expirations or network firewall restrictions, before they impact your production throughput. Effective load balancing depends heavily on the configuration of concurrency limits, which dictate how many desktop flows can be processed simultaneously on a single machine. While some machines may be powerful enough to handle multiple instances, others might be limited by resource constraints or application licensing that prohibits parallel execution. Within the machine group settings, you can define these concurrency parameters to ensure that you do not saturate a host, which often leads to performance degradation or UI automation timeouts. Elastic load balancing leverages these limits to intelligently route requests to machines with available capacity, ensuring that work items are processed in a timely manner. This configuration strategy directly influences the responsiveness of your automation ecosystem and is a primary consideration when designing for enterprise-grade high concurrency scenarios. In troubleshooting issues within a machine group, the primary diagnostic information is retrieved through the cloud orchestration dashboard that keeps track of heartbeats and task dispatching. If a machine remains in a transient state or consistently refuses to accept new incoming jobs, the first step is to verify that the Power Automate Machine Runtime app is active and correctly authenticated with your environment. Network-level problems often manifest as intermittent availability, and this is where monitoring logs prove their worth. You should regularly audit the registered machine list to remove stale entries that no longer represent physical or virtual assets. Keeping your inventory clean and your concurrency settings well-tuned is the hallmark of a resilient and well-maintained RPA infrastructure. See you in the next lecture. Welcome back. In this session, we will establish a rigorous operational monitoring framework to ensure your automated digital workers remain stable and compliant with business service level agreements. Operational monitoring is not merely about checking if a process finished. It is about maintaining a holistic view of the health, reliability, and efficiency of your automated ecosystem. When you deploy desktop flows at scale, the primary concern shifts from initial development to sustained performance tracking. You must treat your cloud and desktop flow run histories as your primary source of truth for auditing and performance optimization. By systematically reviewing the execution status of every run, you create the visibility required to distinguish between transient network issues and systemic logic errors in your automation scripts. If a run fails, the Power Automate portal acts as your diagnostic window, offering access to input and output payloads that are often the smoking gun for unexpected behavior. Examining these payloads allows you to reproduce the exact state of an application at the time of an error, which is an essential step in modern robust software development. To effectively debug issues that occur during unattended execution, you should focus on the granular diagnostic details provided by desktop flow logs. When a desktop flow fails, you must drill down into the subflow execution history to identify exactly which individual action triggered the interruption. These logs often contain specific error codes or detailed system messages that can be correlated against your internal documentation or official Microsoft support references. It is rarely sufficient to simply know that an automation failed. You must understand the state of the machine and the specific UI element that caused the timeout or exception. Because the Power Automate Cloud Portal aggregates these logs, you are effectively performing remote diagnostics on your digital workforce. Downloading execution details allows you to archive this telemetry, which is vital for long-term trend analysis and preventing the recurrence of similar failure patterns. Once you have identified the source of a failure, the operational mandate is to perform a root cause analysis and then remediate the business process. Many developers mistakenly believe that simply clicking retry is a sufficient operational strategy, but this ignores the underlying data issues that often cause failures. Before triggering a rerun, you must inspect the input payloads to determine if a specific data format change or a missing value caused the system to crash. If the input data is the culprit, you can correct it and resubmit the transaction directly through the portal, provided you have configured appropriate retry policies. This cycle of monitoring, identifying, and rerunning is the foundation of a resilient digital workforce, ensuring that even when errors occur, they do not result in significant downtime or backlogs for the business side. Beyond reactive debugging, a mature monitoring framework requires proactive visibility afforded by custom dashboards. Microsoft Power Automate provides native analytics, but you can augment these by exporting diagnostic data into Power BI to construct a real-time health index for your automation environment. By tracking metrics such as average run duration, success rate percentage, and frequency of specific error exceptions, you create a tangible baseline for your service level agreements. When you can quantifiably demonstrate the performance of your bots to stakeholders, you shift the perception of RPA from an experimental pilot to a reliable enterprise utility. This empirical approach to monitoring ensures that your production automations remain aligned with business requirements, even as technical environments evolve. Consistently measuring these KPIs helps you identify performance bottlenecks before they escalate into high-priority incidents that disrupt operational continuity. As you build these monitoring frameworks, always remember that data transparency is your best defense against technical debt in your automation projects. By standardizing the way you capture and read log files, you reduce the time your team spends context switching when an automation triggers an alert. You might consider implementing custom logging within your Power Automate desktop flows themselves, such as appending critical state information to a centralized SQL database or a secure SharePoint log file. This additional layer of detail supplements the native logging capabilities and provides a more granular view of logic flow that standard platform logs might overlook. Integrating these practices into your daily operations ensures that you are always in control of your digital agents regardless of their complexity or scale. I will see you in the next lecture. Welcome back. In this session, we will examine how to extract actionable intelligence from the Power Automate analytics dashboards to monitor and improve our RPA implementations. When we deploy robotic process automation at scale, the code we write is only one component of the overall success of the initiative. We must concern ourselves with the operational health of the infrastructure. just as we would with any other distributed system. Microsoft provides a set of out-of-the-box analytics dashboards within the Power Automate portal that serve as our primary window into these execution metrics. These dashboards aggregate data from Dataverse, providing a holistic view of our automation landscape. By looking at these reports, we gain visibility into success to failure ratios, which are essential for identifying unstable processes that might require refactoring. If a specific flow exhibits a high failure rate, it often points to brittle selectors or unhandled edge cases that our exception handling logic has missed. Relying on anecdotal evidence to manage infrastructure is a common mistake that leads to poor resource allocation decisions. Beyond simple error rates, we need to focus on machine utilization, which is often the most critical metric for proving return on investment to business stakeholders. These analytics allow us to track how much time our virtual machines spend idle versus executing tasks. If we find that machines are frequently saturated while processes are stuck in queue, we have a clear indicator that we need to scale our infrastructure. Alternatively, if utilization is consistently low, we are likely over-provisioning, which results in unnecessary operational costs. These trends over time help us plan for capacity upgrades with precision rather than guesswork. We examine the duration of executions to detect systemic bottlenecks, such as slow-responding legacy applications or network latency issues that affect flow timing. Analyzing the duration variance helps us understand whether our performance issues are intermittent, perhaps due to system load, or constant, suggesting a need for architectural optimization. Connecting these metrics to Dataverse telemetry provides the deep level of granularity required for professional-grade oversight. Since all orchestration data resides in Dataverse, we can leverage that data to perform custom reporting if the built-in dashboards do not suffice for specific organizational requirements. We want to identify the relationship between the number of runs and the consumption of service credits or licensing units. By aligning these technical metrics with business processes, we can calculate the tangible operational return on investment. This is where we shift from being mere automators to becoming strategic partners who understand the financial impact of our work. Leadership does not care about the technical complexity of a selector. They care about the throughput of a business process and the cost per execution. We use this data to justify the transition from attended to unattended automation, or to advocate for additional investments in our automation pipeline. Effective monitoring is not a passive activity, but an integral part of the development lifecycle. We should review these analytics during each sprint or milestone to ensure that the real-world performance matches our design assumptions. If an automation consumes more resources than planned, we treat it as an efficiency bug that requires resolution. This continuous feedback loop ensures that our systems remain responsive and cost-effective as the volume of work grows. By tracking execution trends over time, we also prepare for seasonal spikes, allowing for proactive machine group configuration adjustments before a bottleneck actually occurs. Understanding these analytical patterns allows us to maintain a stable, high-performing environment that scales gracefully. It is our responsibility to ensure that the automation ecosystem remains healthy, observable, and fully aligned with the operational goals of the organization. See you in the next lecture. Welcome back to the concluding review of our journey through the Power Automate RPA landscape. In this final discussion, we will synthesize the architectural, development, and administrative pillars of the certification to ensure you are exam ready. To succeed in the PL-500, one must move beyond mere mechanics and grasp the interplay between cloud orchestrations and desktop executions. We have spent significant time examining how cloud flows provide the governance and trigger mechanisms that delegate heavy lifting to desktop flows, which is a core architectural pattern on the exam. You should be prepared to identify when to use attended versus unattended modes, as this decision dictates licensing, security context, and environment configuration. Remember that unattended scenarios mandate the use of machine groups and the specific infrastructure requirements of the on-premises data gateway. When considering these deployments, always link them back to the necessary service accounts and the principle of least privilege, as governance is a recurrent theme in the testing suite. Data extraction and selectors remain the most granular technical challenge you will face during the desktop flow segments of the examination. You must be comfortable distinguishing between static and dynamic selectors, knowing exactly when to utilize wildcards or index offsets to maintain resilience in the face of changing UI application states. Do not underestimate the importance of the SPY tool and the configuration of UI elements, as these are the building blocks of any reliable automation. Beyond simple recording, the exam expects you to demonstrate proficiency in manipulating complex data types, such as lists and custom objects, to pass information between disparate systems. Practice the mental model of mapping inputs, where data flows from a Cloudflow trigger into a desktop flow, and how to effectively structure outputs for downstream processing. Exception handling is the difference between a brittle script and a production-grade automated solution. You should be intimately familiar with setting error handling policies at the action level versus using try-catch finally blocks at the subflow level. The exam will likely present scenarios where you must decide whether to continue execution, retry an operation, or throw a custom exception based on the specific business failure mode. Think about how you would implement a modular subflow architecture to handle logging, as this improves maintainability and satisfies the requirement for proper audit trails. Debugging is not just about fixing immediate failures, but about architecting systems that are observable and capable of recovering from transient issues without human intervention. Application lifecycle management for Power Platform is a vast topic that warrants high-value focus as you prepare to sit for the test. You need to understand the migration process from development environments to production, specifically how environment variables and connection references act as abstractions to bridge the configuration gap between tiers. Mastery of solution-aware components is mandatory, as this ensures your desktop flows and cloud flows can be packaged and transported consistently. Be prepared to explain how managed and unmanaged solutions function in this pipeline and how to manage dependencies between solutions to prevent deployment failures. The orchestration of machines via machine groups and the monitoring provided by the Center of Excellence tools are the final layer of this administrative stack. When approaching the actual certification questions, read the requirements through the lens of a solution architect. Microsoft often embeds constraints within the scenario, such as specific compliance needs or existing infrastructure limitations, that disqualify certain technical paths. Pay close attention to the phrasing of most efficient versus simplest implementation, as these subtle distinctions determine the correct response. We have covered the theory of API connectors, AI Builder integration, and Dataverse entity management, all of which often appear in case studies requiring you to choose the correct integration pattern. Use your remaining study time to map your current hands-on experience back to the specific performance domains outlined in the official exam guide. Keep your focus sharp as you review these core domains for the final time. See you in the next lecture.